Good morning, San Jose and the United States. Good afternoon, Athens. Good afternoon, Capri. Good morning and afternoon to our viewers worldwide. At the conclusion of today, we will have officially come full circle with our 3-day Artificial Intelligence in Action Forum 2022. And although we won't be patting ourselves on the back, we do have the sense that we have embarked on a meaningful undertaking that the academic, scientific, business, and the community at large have embraced with zest. And we see huge potential ahead, especially after yesterday's intense focus on the practical, meaningful, and palatable applications of artificial intelligence, through so many facets of life. So off we go for our third and final day of the forum. Space, once again, and decentralized finance will take center stage today. AI has proven its great potential and the fact that it can become an absolute game changer in space exploration. And as to decentralized finance, well, finance makes the world go round, and we have been experiencing, at least over the past decade, what it means to be living in a world of centralized finance. And this is certainly not an efficient proposition if we wish to give money the power it deserves and make its uses more efficient for the purposes towards which it is intended. Always, of course, within a secure environment governed with a strong semblance of order. So let's move on to our third day and to our various speakers and the flow of ideas that they bring to the table.
Thank you, Despina. Good morning and good afternoon from Silicon Valley, California. I thought I would begin with a little bit of a background about Silicon Valley. And if you look at the history of Silicon Valley, it's based on the triangle between the educational institutions, the local universities, the government, such as NASA, NOAA, or DARPA, and the defense industry, such as the Lockheed Martins, the Northrop Grumman's, the Raytheon corporations, and so on and so forth. So this triangle, the governmental, educational, defense industry, is really what sparked Silicon Valley and brought the risk and opportunity that was needed to attract venture capital investment. And it's been a growing community for the last multiple decades. It's a model that's been trying to be duplicated worldwide, but it's very difficult and challenging. And Silicon Valley has become from the backbone of technology of the United States. Now it's become the backbone of technology on a global scale. In today's sessions, you realize that we have participants from all these three sectors, the education, the government, and the defense industry, as they literally compose what we consider to be Silicon Valley. Today's Friday, and Friday is a very relaxing day in Silicon Valley. Everybody goes out for long breaks and dinners, and there's discussions about opportunities, technologies, investments. And we'll keep it very dynamic, very interesting for everybody. And it's going to be multidimensional, multidisciplinary, multi-generational. You're going to see the young professionals, the interns, and starting their careers in the space industry versus the professionals, the well-established, with tremendous track records. And at the end, we'll have a surprise for you. We'll have probably the center block, one of the center blocks of Silicon Valley, Woody Gibson, which I'll introduce at the end of the session here. And Woody is the father of clean tech, and now he strives to be the father of space tech. A few words about space systems. If you consider any space architecture, either a spacecraft or aircraft or a satellite system or a mission to distant planets, that's typically a composition integration of multiple subsystems that involves multiple disciplines. It could be aerodynamics, orbital mechanics, guidance, navigation controls, loads and dynamics, nonlinear dynamics, and the list goes on. So it truly requires a multidisciplinary understanding to integrate a complicated system such as that. So the system of systems, it's really what we have been doing for multiple decades. And that requires what we call systems thinking. So since we're in Silicon Valley, we have led the way, and I think Marcus will make some excellent demonstration and points here, in space qualification by leveraging the state-of-the-art and best-of-class subsystems by leveraging Silicon Valley's technologies. So we're going to scratch the surface, though, because this is a very deep subject. And with this, I would like to kick off our first presenter. So I will be introducing my dear friend for many, many years, Marcus Murbach. And of course, if you look at Marcus' bio, it says principal investigator of the SOREX, suborbital and technology education satellites, and so on and so forth. Mark has been a pioneer in the space industry, but his contributions to the space program is much more profound and much deeper than what he's going to be showing you today, I believe, because he's been involved in multiple planetary missions and also entry, design, and landing technologies, which is, as JPL calls it, 15 minutes of terror. The most critical part going from 20 times the speed of sound to landing a spacecraft on the surface of a planet such as Mars or other destinations. So Mark, I think, will impress upon you. He's also an adjunct professor at San Jose State University and Stanford University. But there are two things you will not find in your in his bio. And these are very important items. Number one, he's been the mentor in guiding and directing multiple generations of young kids. Some of them you'll see here, but we're talking probably, I don't know, 10 generations or more who now have become professionals and they power the space industry. And Mark has a doctrine, and the doctrine, I'm sorry for the strong words, Mark. The doctrine is you have to get your hands wet, hands-on, and DBF meaning design, build, and fly. And we're not afraid of failure because failure leads to success. And that's the way, that's how it goes. And you see that in the industry. You've seen that on SpaceX, and guess what? One of the lead senior directors, managers at SpaceX is one of our former students here, and I think he's following Mark's doctrine here very closely. So with this introductory remarks, please join me in welcoming Marcus Murbach.
Thank you, Periklis. That was very gracious. I've had the honor of working with Periklis for a number of years on a variety of projects, and we always seem to advance things and get ourselves in trouble. Okay, so now starts the 15 minutes of terror that Periklis promised. So if I could bring up the slides, please. Okay. That's wonderful. So the title of the talk, this is actually, the talk will sew together some of the presentations that we had in our first space session 2 days ago. And then this will be a splendid introduction to some of our colleagues that will present after me. So the title of this is basically TICASAT 13, which will talk about the first flight of a neuromorphic processor. And I'll explain that the importance of this is the nanosatellites and their advancement of AI, ML, machine learning to space applications. That'll be the general theme. So we'll go see if I can. Okay, quick abstract. So I'm going to go really quickly. Oddly enough, I didn't practice it, so I can't read my slide quite as well as I was hoping. Basically, the feature is here. If you really look at this, the title of it was Aerospace. That we have two things that are currently in the news. One is a Switchblade, which is basically this mortar-fired drone that has amazing, I think, AI machine learning capability on board. It hovers, it does energy optimization, and eventually it chooses and finds an appropriate target and destroys it. And the counterpoint to this is the Ingenuity. This is the nanosatellite-sized drone. It's a helicopter drone that's currently flying on the surface of Mars for exploration, and that greatly enhances the exploration of fixed or ground vehicles, as you can see. So we see the bifurcation or the joining of the two, and that's happening right now. And let's hope, as you know, long as the good guys have the switchblades first, but let's see what happens. Okay, could you flip the slides? Okay, I'm going to build real quickly. The relevance of the nanosatellite is rather remarkable because this is something that just did not exist for us even 20 years ago. And it's a confluence of a variety of disruptive technologies. So disruptive technology disrupts the status quo or the orthodoxy. And the nanosatellite has been a platform to rapidly develop, test, and perhaps go against orthodox principles of our satellite design and whatnot. And the result of that is a splendid advancement of technologies that you'll see. And a lot of this is going to be the confluence in here we are, in the space environment and exploration. Well, first of all, typically launch vehicles, they're expensive. You have a payload, and which is anathema to bring something that's going to pose a risk to the satellite. So the first thing you need is a containerized cargo. You need a way to transport this. Very much analogous to the containerized cargo paradigm that evolved in 1956 that our colleague Angelos would know very, very well about. That reduced the cost of transporting goods by a factor of 2 orders of magnitude. And we see that. So for us, the containerized cargo is this peapod device that you can see here. So I'll bring it up and I'll then hide it momentarily. Oops, there we are. Can you move the camera a little bit, or shall I move? There it is. Okay, this is it. This is the small containerized cargo for the space industry. This standard set of interfaces. This is what allows us to actually transport things, and I'll talk more about it momentarily. So okay, thank you. And the next element of it is we need to have we have a CubeSat form factor, so it has to fit in this box. The box and the thing that fits inside have to match the same interfaces, et cetera. And I'll talk about that momentarily. So this was the beginning of this, and it was contrived by 2 colleagues of mine formerly at Cal Poly University. Well, let's go down the list. iPhone. The iPhone also shows up in 2007 in Silicon Valley as well. So we have one of those, of course. Everybody has these now in our back pockets. But this also represents a confluence of easy connectivity to Wi-Fi, but also the MEMS electronics inside really advances everything. And it turns out a lot of what we fly in here are commercial off-the-shelf technologies that were inspired by this, and we shove it into here. But you'll see another display of this momentarily. What else do we need? We need power. We need power storage. Somebody's calling me. Why would they do that? Forgive the interruption. So power storage, the disruption is actually the lithium-ion cell technology. What we have here is an 18650 battery. It's 18 millimeters by 650 millimeters. So if you have 4, 6, in our case, 16 of these cells, you perhaps have a camcorder or a nanosatellite. If you have 7,200 of these, you may have a Tesla. Okay, so this has been profoundly disruptive. We find them in here as well. I'll put that here. We take this one step further real quickly because in order to make those safe to fly, then we put them in a camcorder battery format. And this is very useful because the space station people allow us on the space station if we adopt something similar to this. So we don't fly without these camcorders, batteries, packs. And so what we essentially have are orbiting camcorders, if you will. So those are the technologies. Okay, so to add, we need a way to talk to these little boxes. There's been revolutionizing technology in that as well. One of the things that we pioneered was the use of the Iridium modem. So we put these in our little boxes, and then our boxes can talk to the Iridium satellites. Or they could be Globalstar, but Iridium in this case. And there we are. So that's the other element of it. That you can barely see, quite small. One that I also mentioned is the COM. Another part of it is that the software-defined radios that we use are also about this size as well. So what else? We have Wi-Fi also developed very, very recently, extremely disruptive, as we know. We take that for granted. And finally, the internet. But the bottom part of this is the confluence is that now we basically have let's start pulling this out. Stanley, we need to shorten this fastener. All right. So here we are. So basically, what pops out of this little containerized cargo CubeSat. So that's our CubeSat form factor that you can see there. Now, what's really interesting about this one, and I'll remove our containerized cargo and I'll put that over here, is that if we look, this is the 10 by 10 by 10 centimeters, which fits very nicely in the containerized cargo. And if you notice, actually, we have a bunch of these batteries in here, which are in fact the 18650 batteries. If we look deeper inside, there is actually a smartphone. This was in fact the first of our phone sat series at NASA Ames. And while it didn't do very much at first, it did actually inspire several companies in the new space industry. And from this, we started growing, adding more capability over the last 10 years or so. The Planet Labs, our colleagues over there in that company, basically were involved very much in this, and it spawned this. So this gives you a quick idea of how rapidly things have come together and how this is a confluence of disruptive technologies. Back on my slide, I wanted to mention that actually one of my esteemed young colleagues over there that actually helps drive and builds all this, we discuss, she can actually command the nanosatellites that we have up there with a neuromorphic processor by essentially sending a command to the Iridium from his smartphone over Wi-Fi. So that's how everything started to connect. Okay, with that longer than necessary introduction, I'll put this aside for just a moment. And let's go on to the next slide. Could you flip? I have a problem with the iPad. Thank you. Our team has been building satellites, suborbital test vehicles for a number of years. That's what we do. We've been able to keep a very rapid cadence. Part of the acceleration of technology development is rapid feedback. We have to learn very quickly by our successes and our failures. And so by having a rapid cadence, what doesn't work quite well on one flight then gets essentially upscoped, as we call it, in the subsequent flight. And so we've been doing this for a while, and it's at the very bottom right, you see our crew 3 weeks ago at the at Vandenberg Air Force Base, where we were integrating our TicketSat number 15, the 15th version of this. Next, please. We're busy right now because we're a rapid flight development team, a skunk works within the government, if we're permitted to use that phrase. We deorbited one earlier this year. That was actually TicketSat 7. It was the first Virgin Orbit flight. And TicketSat 13, which has the first flight of a neuromorphic processor that you'll hear about momentarily, that went up in January. We're building 2 more. One is due in August. The other one is due in December, fairly rapid cadence. We're always looking for rides. There's sometimes availability with slots if other teams happen to drop out. So anyway, we're very busy people, but we've landed right in the middle of this new space launch arena. So we've launched on Antares, on Virgin Orbit, on Firefly very shortly, now on Astra in a few months. Next, please. Okay, so our team, we are a nano orbital workshop, so we have a lot of collaborations with our colleagues in industry, also academia. So we work with several different universities and very much with Periklis and his teams at San Jose State University, which I'm honored to be involved with. But we've done a variety of things. We were the first nanosatellite, CubeSat, off the space station, which was a wonderful and longer story. And then we elongated these. We eventually flew a long version of this off the space station, looking at eventually autonomous navigation and reentry point targeting. So we're looking at that. The suborbital rocket you see on the lower left. And finally, we've been interested in Mars exploration. So actually, Dr. Papadopoulos and I proposed CubeSats on the surface of Mars and also the moon. The one you see over there looks like Mars. It's on the Atacama Desert. It's a 3U nanosatellite with wheels. It actually works very well. We call that proposal atromos, which is the Greek word for fearless. So we hope to fly something like that in the next few years. Next, please. Okay, so what our current Test 13 hardware looks like is the following. So this is a rendition of it, but it's more complicated. When we actually add all of the wiring, cabling, harnesses, then it looks like a Medusa. And we have to, the integration is very difficult or challenging in calculating. So we do this, it fits into a longer box. And the ones that we're building now, we double in width so that we can actually build dual stacks. I'll mention that momentarily. Next, please. And there we have it lying on the table. So this was our 3U, and lower left, you've seen this picture from our colleagues the other day. This was our Virgin Orbit flight, the first one that was successful. And we're very happy with that. Actually, we've been on Virgin Orbit now twice, this one with the Test 13. And then you see it with a unique drag device that is deployed in the lower right-hand image over there. And we're very interested in minimizing space debris. So one of our research paths actually is how to build these drag devices we call exobrakes to either dispose of debris or guide them to the proper reentry point. Next. Okay, and then this confluence is really interesting. We're very excited to work with our colleagues within NASA and Intel and Air Force to actually fly the first neuromorphic processor. What it does primarily, it is able to do a lot of, let's call them calculations on very unique problems like image recognition, machine learning, very quickly with very, very low power. And that's a great confluence with these small nanosatellite platforms. So in the coming years, we're going to see, as we are learning to use these and advance this and disseminate this information, we'll see more and more of this used in private industry. You'll be able to do much more with optics, neuromorphic processors of different sorts and whatnot. And our colleague, Dr. Garrick Orchard, will follow me shortly and go into this in more detail. Next. In developing the AI machine learning payload, we had a short amount of time to be able to do this, but rapidly came up with a fairly unique interface from which we're now building upon my colleague in the audience. Alex Salas was a key architect of this, along with Eric Barsh. And so we're advancing that. We learned a lot from the first iteration. Now we're looking at the next two and how to plan these, make them even more facile in order to run unique scripts, unique machine learning algorithms. Next. I'm popular this morning. Okay, the software interfaces, again, a lot of detail went into how we do this. It's command and control through actually one and then later a second Iridium modem. So we use a lot of this in order to turn the brains on. And let's go on. The software environment is it's at various different levels. To give you an order of magnitude, there's about 10,000 lines of code that went into our little box. A lot of it from libraries, but a lot of it had to be tested. The interfaces, the software interfaces had to be tested on how they work properly. And gradually we're evolving from that again, as I mentioned. We want to expand upon this, but the mechanical, electrical, and particularly the software interfaces through the comm systems are really key to our success. Next. And the radio. So I talked about our software-defined radio. We call that actually our lunar radio because we want to actually use that and eventually our Mars radio for other planetary missions and flights, etc. But here we have it's an S-band. It's a QPSK format. You can see that on the right. It has 4 different quadrants. This was an example of our flying over the Amazon Web Service site as well as NASA Wallops. Where we are working with them in order to actually extend comms concepts to the lunar orbit and lunar surface in a short time. But this is also another viable part of the experiment. Next. So I just wanted to briefly point out that previously from the space station, we've dispensed with a very much larger 6 or 7U nanosatellite that was basically about this long, as you can see there. And that had all kinds of experiments, but the one I wanted to highlight was we were also interested in flying the NVIDIA GPU. So for us, this is like flying a supercomputer in a nanosatellite format. It does require a lot more power, but our interest in that is that we'll be able to perform experiments with the Google TensorFlow environment. And so we're now, in one of our next flights, we'll combine both the low-powered neuromorphic processors, for example, from Intel, and also our colleagues at NVIDIA to fly a specific Jetson TX2. Next, I think that's a beep to tell me I should hurry up. Next, just these are some just numbers, but they're really initial results, looking at the statistics of how well our different scripts ran. So we're collecting those as we go along. We learn from them, and then we're evolving those into our next satellites. Next. Concluding thoughts. So in many aspects, the AI in space is already here. It has been, and we saw some examples just very quickly in the aerospace, both for defensive and for exploratory purposes. So that's important. We introduced these nanosatellite as an important platform, is itself a pyramid, a confluence of a bunch of important disruptive technologies that make this also a disruptive technology. Because of the rapid feedback development, we can advance technologies a lot quicker. The AI ML so far has been quite successful. We learned from that. We plan, now we're building a dual stack in our next set of nanosatellites in the next few months, flying those on new space launchers. So we're very excited about that. And our future flights are going to be basically the ones coming up on Astra, on Firefly, and also Virgin Orbit. So all that's coming together very nicely. Again, we look for collaborations, and it's been a lot of fun. The last little note I wanted to make is that on Test 13, we also involved the interest of a dear colleague of mine, Janet Biggs, who's an artist, and so we have actually a piece of art on that, and she will include that in one of her next art exhibitions. So not only is it just the advancement of technology and all of that interest, but looking at the artistic aspect of it and exploration and everything else, just the essence of being human and exploring as we counter our interests in artificial intelligence and machine learning. Thank you very much.
Hello, ladies and gentlemen, once again from Athens. We now turn the spotlight, of course, back to San Jose to discuss NASA's autonomous systems and to hear some views on a couple of questions. Two of them that come to mind as we speak is, do we have autonomous tools to operate space vehicles without assistance from mission control? That's one issue we'll hear about right now. And how do we envision that developments in artificial intelligence will enable future exploration missions of NASA? Join us for this very engaging speech and discussion. Thank you.
I have the pleasure of introducing Dr. Jeremy Frank, who is the group lead of Planning and Scheduling Group in the Intelligent Systems Division at NASA Ames Research Center. He received his PhD from the Department of Computer Science at the University of California at Davis in June 1997. He also has a BA in mathematics from Pomona College. Dr. Frank's work involves the development of automated planning and scheduling systems for use in space mission operations, the integration of technologies for planning, plan execution, and fault detection for space applications, and the development of technology to enable astronauts to autonomously operate spacecraft. Dr. Frank has published over 70 conference papers and magazine articles, 10 journal papers, and 3 book chapters, and received over 40 NASA awards, including the Exceptional Achievement Medal, the Silver Snoopy, and NASA Engineering and Safety Center Award.
All right, good morning, everybody. Thanks for coming. And let's see. So thanks for the introduction. And before we get into the main part of the talk, I want to provide some motivations. This is a picture of Phobos, which is one of the moons of Mars. This picture was taken by the Mars Reconnaissance Orbiter in 2008. So imagine, if you will, that there is a spacecraft in the vicinity of Mars orbiting near Phobos, and there are humans on board. This is the first human exploration of Mars. This would be the crowning achievement of human spaceflight in our lifetimes. So what I'd really like to tell you is that this is NASA's current vision, and that this is what we're actually on the cusp of doing. Alas, I can't do that, but we're doing something almost as good. NASA is currently engaged in what's called the Artemis program. Artemis is a plan to send humans to return to the moon in preparation of someday going to Mars. What I have here is a notional schedule for the human return to the moon. This is work that's been ongoing for several years now. What we see across the top is a progression of flights, including what is referred to as Artemis 1, which will be the first human-capable spacecraft to return to the moon. That will be followed by Artemis 2, which is the first humans to return to the moon in the 20th century. Artemis 2 will conduct a mission somewhat like Apollo 8. It will take humans to the moon. They'll fly a figure 8 around the moon, and then they'll return to Earth. But this in turn will set the stage for future human return to the lunar surface. That in turn will be aided by something called Gateway. Gateway is a human-occupied space station that will be in lunar orbit. Gateway is being built as we speak. And the plan is that humans will fly to Gateway, and then they'll be able to come to the lunar surface and conduct exploration missions and walk on the moon's surface, much as we did in the 1970s during the Apollo program. In conjunction with this, there'll be a series of surface missions. There's a program called the Commercial Lunar Payload Services Program, which is going to put scientific instruments and various payloads onto the lunar surface. You see that at the left. And then in the middle, you see a variety of surface habitats, lunar rovers, and various other assets, all of which are going to return to the moon. And this is what comprises the Artemis program. So with that as motivation, the first thing I'm going to talk about is human spaceflight mission operations and mission operations functions. This is how we conduct space missions today. And I'm going to use that to set the stage for the use of artificial intelligence in order to enable autonomous operations on the lunar surface, and again, in preparation for going to Mars. I'll then say a little bit about what some of the relevant technologies are, planning, plan execution, fault management, and some associated technologies. And then finally, at the end of the talk, I will provide some information about a couple of experiments and technology development activities similar to what we just heard Mark Murbach talk about. And scheduling is the ordering of tasks in order to satisfy a variety of constraints. And we're going to talk about what some of those constraints are here in the rest of the slide. So one constraint that may exist that needs to be satisfied is a constraint on time. When can I accomplish some task? So if I need to take a picture, and if I take the picture too early, say before 10 o'clock, the image will be too dark. If I take the picture too late, after 10:30, the image will be too bright and it won't be satisfactory. So this is an absolute time constraint on an activity to say, take an image. I can have relative time constraints between a pair of activities. So if I have an activity to rotate or slew my spacecraft, it may take 5 minutes for the attitude control system to stabilize the spacecraft, so I don't want to take my picture until 5 minutes afterwards. I can have a variety of resource constraints, say the battery state of charge must exceed 65% in order to have reserve power. I may have mutual exclusion constraints. I can't operate two instruments at the same time. I can have additional constraints that satisfy this goal achievement that we talk about in planning. These can include preconditions. I have to have power on to my instrument before I take a picture, or it may be the effects of actions. I achieve a goal, I took my picture, but I used memory. So these are the kinds of things that planning and scheduling systems, of which there are a great many, this is what they do. Next slide, please. Plans are no good unless you can execute plans. And this is the purpose of software or technology to perform what we call task execution or plan execution. The functions that we talk about here are primarily focused on discrete tasks, starting tasks, stopping tasks, choosing task orderings, responding to contingencies. And this is distinguished from continuous control at a much lower level and on a much faster timescale. So in order to use task execution systems, plans need not just to be a sequence of tasks where you do each task in turn. They can be much richer control structures. They can resemble programs, so there may be branches, there may be loops in order to try tasks multiple times. In addition, you trigger monitors in order to watch a task and be sure that it's doing what it's supposed to. The task execution system can delay the start time of a task until all the other conditions are achieved. And so there's a rich set of functions that the task execution system is responsible for. Next slide, please. So the next item we're going to cover is fault management. Fault management is what you do when your spacecraft is having problems. You monitor systems to determine whether a fault has occurred. If a fault has occurred, or if you believe one has occurred, then you have to do fault detection and fault identification, because faults don't come in single spies, but often they come in battalions. And so it may be required to isolate faults to a single root cause. But another most important function in fault management is to assess the remaining system capability. And an example I like to use to illustrate this is that a light bulb has gone out on my spacecraft or in my house. Well, the consequences of having lost a single light bulb may not be all that interesting. So even though there is a fault, it may not jeopardize my mission. On the other hand, if I've lost power distribution to half of my spacecraft, well, I've lost a lot more capability, and my mission objectives may be threatened here. And so that characterizes this fault consequence assessment function. It's also useful to compute loss of capability, i.e. I can't actually execute my mission at all, versus loss of redundancy. These are things that we care a lot about. And so that's the integration between all of these different fault management functions. Next slide, please. So those three technologies are the key technologies that I've explored in most of my work. And there are a variety of associated technologies that accompany the AI core. So when we build decision support systems for astronauts, these involve the creation of human interfaces. I need to present my plans, my fault detections, my fault isolations, and my mitigations to people. And so that requires designing user interfaces, figuring out how people can absorb all of this information that the AI is providing. You can think of that as sort of the upward integration story of all of my AI. There's a downward integration story as well, which is the integration with flight software. I need the AI to understand the data that's coming from the flight software bus. I need to be able to send commands to systems in order to actually get the spacecraft to execute my plans. So we need to get that integration story right. When we're running our AI in space, even on a human space flight, we're compute limited, we're resource limited. So we need to take into account developments in high performance in space computing, because many of the AI applications are very resource intensive. So last but not least, we'll talk about machine learning. So we heard some great things from Mark Murbach about the use of some of these neuromorphic chips. It's, I think, a little bit far in the future to imagine that we're going to be doing online learning on a human spacecraft, but we do want to take advantage of using machine learning and to execute classifiers, in other words, the output of machine learning, on board our spacecraft of the future. This introduces a variety of challenges in terms of verification and validation in order to ensure that my learned classifier does what it's supposed to, and that I have confidence in its results. And if we go to the next slide, that speaks to some of the integration and system engineering challenges, as well as some of the human interaction challenges that we have for building these systems. Many of these AI systems were developed in isolation. We've never had to integrate them with each other, let alone with human interfaces or flight software. We talked a little bit about the challenges of in-space computing. So there are a lot of development challenges that need to be addressed in order to make effective use of all of these technologies. Next slide, please. All right, so for the last few minutes here, what I'd like to talk about is some specific development test projects that we've been performing over the last several years in order to mature technology for use in human spaceflight and collect lessons learned. Next slide, please. So the first of these was a demonstration of crew autonomous operation of a system called TOCA. You see in the center picture on the right, an astronaut is holding an iPad and he's floating. You can sort of dimly see it. He's floating above a piece of hardware set in the quote unquote floor. This device, the TOCA device, is a water quality analyzer. The crew use it to check the potable water quality. They do tasks to either check the water or maintain the TOCA hardware a couple of times a week. Those tasks are currently scheduled by mission control. What we did was we wanted to see if crew could take responsibility for managing the TOCA, which includes planning the tasks. So you see at the bottom a task planning window. This is where they used to identify tasks that they needed to perform for the TOCA hardware. We also wanted to evaluate the crew's ability to determine whether the TOCA was working right or not. So there is fault management and anomaly detection built in. We deployed this on ISS for about 7 months. It worked very well. We learned a great deal of lessons learned, and that was also a case where we had to build some user interfaces in order to make sure that the crew knew what the underlying AI was telling them. So again, that was a great experiment. We learned a great deal from that work. Next slide, please. Another activity that we did on board ISS was to have the crew manage a system automation. So what we see in the bottom right here is a picture of what's called an express rack. The express rack is a piece of hardware that allows payload developers to create completely self-enclosed physical and biological sciences payloads. You see one of the payload drawers in the bottom of that image. But the rack itself is very complex. It takes 3 flight controllers on Earth, 45 minutes to power up and configure that piece of hardware. So the challenge of this demonstration was, could we have a crew person on board ISS power up and configure the rack at the push of a button? And so we built a combination of automation technology and a user interface to help the crew both power up and configure the rack, track the progress of it, and make sure that the rack powered up and configured properly. And that was also very successful. It was so successful that we're doing it for the 3rd time, which means that it wasn't as successful as we'd like. We learned a great deal the first couple times, and we were about to embark on the 3rd repetition of this in order to learn even more lessons in the future. Next slide, please. So a third piece of work that we're doing on board ISS is a little bit of a segue from some of the other AI. We're using augmented reality in order to help the crew do inspection and maintenance procedures. These procedures, unlike electronic procedures, this is where the crew actually has to put hands on hardware. So they have to, engage their hands, which means that they may not be able to read a printed procedure and help them execute the procedure in the event that they have questions. So right now the crew would have to call down to Earth. And so our question that we're exploring here is, can you use augmented reality and computer vision and image recognition systems, as well as procedure execution decision support, to help the crew do things like inspect the T2 treadmill, which is one of the pieces of exercise equipment that they use to keep themselves healthy. So we see some images on the right-hand side showing those activities that are ongoing on board station as we speak. Again, great experiments. We're learning a lot of lessons about what does and doesn't work and how to make this technology better. Next slide, please. So segueing away from technology development and testing on board the ISS, the Advanced Caution and Warning System, ACAWS, this is a technology for fault management that we developed in conjunction with Orion, which is that vehicle that's going to take astronauts to the moon later this decade. So the main purpose of this was to develop fault management systems that would help do fault identification, fault isolation, and capability assessment, loss of capability, loss of redundancy. This was primarily developed with Orion, and you can see some pictures of some tests that astronauts have been doing and flight controllers with the Orion. This was a very excellent line of work. We did this for several years. We'd hoped to infuse it into Orion, and unfortunately we weren't able to do that. But it set the stage for the last slide that I'll talk to here. So go ahead to the next slide. And fault management, as you remember, was one of the 3 sort of pillar technologies that we developed. And so for managing the gateway, both to reduce crew workload and also fusion and fault management, all integrated in flight software in order to manage the gateway. Like I said in the beginning of the talk, gateway is going to be untended quite a long time, 10 to 11 months out of the year. And so the purpose of this vehicle system management is to basically different repetitions of tests and have actually successfully infused this technology into gateway as part of the flight software system. Next slide. So in conclusion, NASA investments in AI have already made an impact in this Artemis program. And a big part of what we want to do now is to continue development of this technology in order to influence future Mars exploration by maturation throughout the rest of the Artemis program. And that concludes my remarks. Thank you very much.
Now, the next question that our speakers are going to answer is, how does Silicon Valley's tech and the latest technologies in quantum computing and the neuromorphic processor support the space program? So let's go back to the Silicon Valley to learn about that.
Hi, my name is Connor Gasky. I'm a recent graduate in aerospace engineering here at San Jose State University, and I have the pleasure of introducing Dr. Garrick Orchard. Dr. Orchard is a research scientist in neuromorphic computing at Intel Labs, where he focuses on bioengineered sensing and processing. Garrick received his PhD in electrical and computer engineering from Johns Hopkins University in 2012, and worked as a research scientist at National University of Singapore from 2012 until joining Intel in 2019. So please welcome me, please join me in welcoming Dr. Garrick Orchard.
Thank you very much for the introduction. Yeah, my name's Garrick Orchard, and as you see on your screen, I'm a senior researcher at Intel Labs here in Silicon Valley. And I'm going to talk to you today about neuromorphic computing at Intel. So I'm a member, senior researcher of the Neuromorphic Computing Lab, specifically at Intel Labs, so we're the research wing of Intel. And so in the Neuromorphic Computing Lab at Intel, we're pioneering this new programmable compute technology that's inspired by our modern understanding of brains. Our goal here is to integrate this brain-inspired computing technology, which we call neuromorphic intelligence, into computing products at all scales. So biological brains have very impressive capabilities. As an example here, a bird can navigate complex, unknown environments at very close quarters and very high speeds while consuming very little power. By comparison, modern computing technologies burn watts or perhaps even tens of watts to slowly navigate a drone through way markers, even in a tightly controlled environment. So there's a lot for us to learn here from biology and apply to computing, and we believe we can apply this at many different scales, not just at kind of the micro aerial vehicle at the edge, but all the way up into the data center. And so we strive to achieve brain-like efficiency, speed, and adaptability and intelligence, while delivering gains that are orders of magnitude higher in the energy delay product for a wide range of intelligent workloads. We'll revisit the energy delay product in a moment. So our pursuit has led us to this new class of a computer architecture, neuromorphic computing. I think most of us are familiar with the old kind of CPU idea where you have a sequential processor connected to memory. This introduces a von Neumann bottleneck, and your programming model here is typically just a sequence of operations that you've handcrafted for the CPU to perform, and this is how you define your algorithm. Whereas more recently, in the last few years, maybe you could even argue a couple decades, we've been moving towards parallel computing, where instead of handcrafting an algorithm, many times you can train it from data, but these are typically large offline data sets that you're training from. And the paradigm here is still a synchronous clock paradigm, but with this very dense, large parallel compute. Neuromorphic computing, which is the direction that our lab is headed in, we hope will offer the ability to learn on the fly through these neuron firing rules. So can we have a model or a computer architecture that doesn't need to be trained by massive offline data sets, but that can learn and adapt to new environments as it is navigating? We take an asynchronous approach to this design. So this is quite a kind of exotic design methodology. We're very familiar with talking about clock speeds of your CPU or GPU, but in our case, of asynchronous, there's no such thing as a clock. And this brings us towards a paradigm that's still parallel computing, but is very sparse. Right? So if you imagine neurons on the brain, there are very many of them. So it's massive parallelism, but at the same time, very few are active at any time. The communication between these neurons remains very sparse at all times. And this is one of the keys to achieving energy efficiency and is very well suited to our asynchronous design methodology, since there's no kind of clock running consuming power regardless of what compute has to occur. So about 3 years ago, we released the Luihi chip. This was our first processor that we released as a research processor to the external community, and our software for it, what we call the NX SDK, our neuromorphic software development kit. We've been building a community around the software and our hardware. Over 150 different labs around the world, spanning academia, many universities, government labs, even Fortune 500 companies, a wide range of researchers and research labs that have been getting hands-on with our hardware and having access to our software. They've been pursuing all kinds of different research directions and helping us to understand just what is the chip good for, where are its strong points and what kind of applications are really well suited to it. And of course, what kind of applications are not so well suited to it. And this is going to be an important thing as we identify kind of the key areas that we need to push on for this technology to succeed. So we've released very large systems, hundreds of chips in a single system for our largest one. So I believe it was about 768 chips, all the way down to applications that take up a small fraction, 1 or 2% of a single chip. So those would be things that are operating at the edge, maybe consuming a small amount of camera data, whereas larger you might have things like simulating very large scale systems with hundreds of chips at once. Quite excitingly, recently NASA did put one of these devices up into orbit on one of their CubeSats. So I believe Mark Murbach, I heard him mention that Intel and the neuromorphic computing that went into the TES 13 payload. So the first version of this chip we dubbed Luihi. Luihi is an underwater seamount in Hawaii, so we're kind of using this naming convention of having a volcano beneath the sea, ready to come up and erupt at any moment now. So we've had significant progress over these last 3 years within the neuromorphic research community, and using Luihi, we've really confirmed the value of this research direction. To give you an idea of some of the examples we've been looking at, one of them has been this gesture recognition and learning example. This is using a dynamic vision sensor on the top left of your screen there. So what you're seeing is in fact me, recording of me performing various actions in front of the sensor and having the sensor classify it live. We extended this a bit and started learning new classes of actions in the last layer online. So using a partially pre-trained model, a user can now deploy this model and dynamically learn new gestures just by performing them in front of the sensor and giving an indication to the device that this is a new gesture that must be learned. We saw advantages in adaptive robotic arm control. So here the task is to reach and grasp and pick up different objects. You can imagine that a robotic arm, as it picks up an object that is heavy, induces some load on the arm, kind of the control mechanism that you'd need and the force you need to apply to keep that arm in a constant position increases. And so without necessarily knowing exactly what that object is or what the weight of the object was beforehand, we showed that we were able to adapt the controller to account for this difference in the load being applied to the arm. And we're able to do so at 40x lower power and double the speed of a CPU. We've seen some exciting research in combinatorial optimization. Here the video playing shows a simple, or fairly simple by comparison, Sudoku problem, but you can certainly imagine us applying similar concepts to far more advanced problems, which I'll show on the next slide. We published some work on olfaction-inspired recognition and odor learning. So this is being able to recognize a new odor that's perhaps masked by many other odors in a mixture with very few samples, in fact, even 1 or 2 samples. And by being able to go to only 1 or 2 samples, we're able to claim 3,000 times more data-efficient learning than a traditional deep autoencoder. Finally, on the bottom right there, we've also done some work on scene understanding. So we're able to show these integrated behaviors of object recognition, tracking, and learning in a simple SLAM application that's achieving 100x lower power than a competing CPU approach. And what we've seen so far is that for the right workloads, we are able to achieve these order of magnitude gains in latency and energy efficiency. So the plot I'm showing here is from a paper we put out last year in the proceedings of the IEEE, and it really gives an overview of all the research we've been doing over the last 3 years and tries to summarize where we see the value and which things aren't working so well. The summary plot, each one of these data points that you see on this plot is an individual example that we've run on the chip, benchmarked, and compared to competing approach. The competing approaches can be CPUs, GPUs, or even other neuromorphic processors. On the vertical axis, we have the time to solution ratio. So here, the higher up we are on this axis, the more advantage Luihi has. In other words, Luihi is performing the task faster than a competing approach. On the horizontal axis, we have the energy ratio, and the further we are out to the right on this axis, the more advantage Luihi has. In other words, the lower power, the lower energy Luigi is consuming compared to a competing approach. And by taking the product of these two metrics, the energy and the time to solution, we get the energy delay product. So anytime we have a data point that is above the dotted oblique line that you see here, it means that Luigi has a better energy delay product. In other words, is finding a solution at lower power and or faster than a competing approach. However, if we're below that line, of which you do see there are some data points on the screen, it means that we're at a lower energy delay product. In other words, Luigi is not performing better than the competing approach. And if we analyze this data a bit, we see some trends emerging. First of all, we see that standard feed-forward deep neural networks, they give us the least compelling gains, if they even give us any gains at all. And this is not surprising. We haven't set out to make a deep learning accelerator or a deep neural network accelerator for the edge. We have a far more general class of algorithms that we can deploy to our chip. And so it's no surprise that when you compare us to devices that are optimized for that specific workload, that perhaps our chip doesn't outperform them. However, we do see enormous gains for recurrent networks. These are networks where you have some network with state internally that's being updated dynamically, and there's just kind of some recurrent connections that that update the internal state. So there's some dynamics at play that are implemented through recurrent connections that update this state over time. The state lives in on-chip memory within the chip, so we don't have a problem going to, say, off-chip DRAM, which introduces the von Neumann bottleneck and slow us down and increase our energy consumption significantly. So for this recurrent class of problems, we see significant gains up to multiple orders of magnitude for Luigi. If we zoom in on the best examples here, we find that many of them are optimization problems, answering questions such as, what features in a dictionary of features available to me best explain the sensory input that I'm seeing right now? Or what is the shortest path to my goal? This can be a literal shortest path on a map to reach a certain location. Or, what is the shortest path that I can traverse that will allow me to visit each of the waypoints I want to visit at least once? So this class of optimization problems is looking very promising for us. Since releasing the paper last year, we've continued benchmarking a number of other problems in algorithm classes. And one of them is using quadratic unconstrained binary optimization and applying it to the example of solving this maximum independent set problem, for which we find gains of up to 4 orders of magnitude in the EDP for Luigi. So the maximum independent set is a generic NP-hard graph problem that's used, for instance, in computational biology. And this quadratic unconstrained binary optimization is especially interesting because it's a generic algorithm that's been the workhorse of it's been the workhorse algorithm behind current quantum annealing approaches, for which other companies are also building special purpose accelerators. So it's a general class of problems that it can be applied to many different areas, and there are other companies out there that have just dedicated accelerators just for solving this particular problem. Here with Luigi, we're seeing orders of magnitude improvement over some of the competing approaches. So we obtained one of the most exciting examples here for solving real-world train scheduling problems based on integer linear programming in collaboration with the German railway company Deutsche Bahn. For which Luigi again outperformed a commercial state-of-the-art solver on the same problem by, in this case, 5 orders of magnitude in energy delay product. So here the challenge was to find train route assignments. So given a customer requests and rail time and train constraints, the task is to figure out, which routes should the trains follow to satisfy these constraints and best satisfy the customer requests. So the same algorithm can also be applied, though, to many other real-time resource allocation problems. So taking all these learnings that we've had with Luigi, we're now developing new software, new hardware, continuing to build our community, and trying to push us into a new era of neuromorphic computing. We believe that the computational value of this approach has been shown, and it's been shown using today's manufacturing technology, meaning standard silicon technology, not going into all these kind of exotic devices, which show a lot of promise further down the road. We found that it motivates a new computational paradigm. Cheap continuous optimization has turned out to be a very promising area for us. And we've managed to deploy many successful online learning applications or many successful learning algorithms. All of them have been quite shallow so far, still work on getting to deeper algorithms, but had significant early progress there. However, there's still many challenges lying ahead of us that I'll get to on the next slide. But some common properties of the suitable applications we see are, power constrained problems where we're also latency constrained. We need to process real-time signals, right? You're reacting to things that are happening in the world around you with as low latency as possible. Slowly evolving structure. This is again thinking about maybe novel environments, navigating into new areas, or environments that themselves change over time. We typically use deep learning for offline training to kind of pre-train a model before we deploy it to the chip, but there we can still benefit from shallow online learning once deployed to our research processor. Some of the challenges and headwinds that we see in this area, one is that there is a fairly high cost of the device due to on-chip memory integration. So the cost of physically having to implement memory inside the chip, all the state of the chip is held in its internal memory. This, of course, increases your silicon area and increases, therefore, the cost of the chip by increasing its size. There are also challenges on the algorithm and programming model side of things. So while there's been a lot of very interesting initial work exploring a wide range of algorithms and programming models, what we really want is not just 1,000 different options of programming models and algorithms, but some kind of convergence on a common set of algorithms and understandings of how you should work with and configure such a device. And so a huge part of that is software convergence. So this algorithm and programming models have extended into software for a long time now, where almost every team is developing their own software framework for configuring their device. So on our side, just recently, we've announced a greatly improved Loihi 2 chip. I'm not going to go into all the details here. Happy to follow up for anyone who wants to go into them. But we're on the cutting edge of Intel's Intel 4 manufacturing technology, which has allowed us to shrink the device significantly. We're at about half the size here of the original Loihi device, yet we're achieving 10x faster circuit speeds. We have increased the capacity, the number of neurons by a factor of 8. We have far better scaling and integration here, so our chip-to-chip links and communication within the chip has also been accelerated significantly, but overall still maintaining the same general architecture, just expanding kind of its capabilities in terms of performance, and it's generalizing the configurability of the device far further than, a few factors in the initial device were fairly hard-coded, somewhat simple computational elements, and here we have a far more flexibility of kind of microcode defined computation within the chip. So we have a greatly improved chip that we're very excited about. We're accompanying it with a new software development framework that we're dubbing Lava. So it's a new software framework for neuromorphic computing. So whereas previously there were a wide range of different software frameworks that were satisfying different individual needs in the neuromorphic computing space, we're hoping to pull these all together under this common open source software framework with permissive licensing of all the core components. The idea here is that we hope the community will step in and contribute. This is going to be an event-based communication software framework, right? It allows you to do event-based communication between simple parallel processes, which we think is an important way to think about neuromorphic computing. And we want the software framework to support multiple paradigms, multiple levels of abstraction for different kinds of levels of user expertise, and to support even multiple platforms, right? So it's important to us that a user can go and deploy these algorithms on a CPU or GPU to develop algorithms initially, and later deploy them to our chip to see, kind of the huge EDP gains that we get out of it. So it's important to us that it's multiple paradigms, supports multiple paradigms, directions in which we're pursuing this research moment. I spoke a bit about optimization, but some of the other interesting areas we're looking at are neural attractors. These are dynamic neural fields, deep learning areas. So can we apply what we know from deep learning to help us generate better models for the chip? And can we find ways to approximate deep learning on the chip itself to improve its online learning capabilities? And a little bit further down the research direction here, we're looking at vector symbolic architectures. These are things where you have, concepts such as compute and memory integrated into these high-dimensional vectors that are incredibly sparse. Our computing framework and chip itself are highly, highly optimized for these very sparse workloads. So we're implementing all of these. We're adding model learning, as associative learning here, gradient-based learning through deep learning, or even high-dimensional learning for vector symbolic architecture using the chip's capabilities. So we're very excited about all these research directions. We're exploring all these different algorithms and applications, and we see an outlook to commercial value where you can deploy this chip at many different scales, right? So from specialized designs right down at the edge, you can imagine a couple of cores serving as a co-processor on a much larger, CPU, GPU, or some other device, doing something like wake on voice detection, dynamic noise suppression, just a little bit of edge audio processing, versus something a bit more intermediate, placing a larger device on a small robot, aerial vehicle that has to navigate and explore and understand its environment, all the way up to the edge where we can deploy scaled up systems in the data center, things like recommendation systems or deploying Luihi for scientific computing and just general high performance computing. So we're excited about all these different research directions. We hope you are too. If you'd like to get involved, as I mentioned, we have this research community, over 150 different labs around the world that are actively using our hardware and software. So to get involved, please reach out to us using this email that you see here. Or if you're interested in the software development framework that we're looking at, there's a link to it here as well, the Lava Neuromorphic Computing Software Framework.
Back to Athens, ladies and gentlemen, to set the scene a little bit. The issue of trust permeates society in so many facets of our lives, and autonomous systems, of course, would be one such facet. And this is what the focus of the next session will be. Two major issues that will be discussed in the form of questions coming from Athens are the following. Do we trust autonomous systems, or do they remain an elusive problem within space systems engineering? That's the one issue you will hear about. And the second one is whether we trust design phases of human-machine interaction when human factors are tested. Join us for this next session. Thank you.
So we're going down the route of Silicon Valley. We looked at, we had presentations from the governmental perspective, from the industry perspective, and as I indicated at the beginning of the session, the three-legged stool of Silicon Valley includes the defense industry. That's a critical contributor in the formation of Silicon Valley. So naturally, we contacted Lockheed Martin, Star Labs, Palo Alto Advanced Technology Center, and the consensus unanimously was, yes, please invite Michael Woudenberg. So with this little introduction, I would say that Michael is a senior engineering manager at Chain Analysis Incorporated, leading the software development of advanced blockchain analytics. Prior, he was senior staff operations research analyst for Lockheed Martin Corporation, and then applied research lead for autonomy, artificial intelligence, and machine learning. His experience also includes program management of cyber, electronic warfare, directed energy systems, R&D portfolios with Raytheon Corporation, Advanced Avionics at Honeywell Aerospace. Michael is also a veteran of the US Army, where he served as an airborne and ranger qualified field artillery officer. Michael holds an engineering degree, master's from Johns Hopkins University, and a bachelor's degree in information systems from Michigan Technology University. Please join me to welcome Michael Woudenberg.
All right, good morning. My name is Michael Woudenberg, as mentioned. Representing Lockheed Martin in the time that we've done this, I have moved on slightly to a blockchain startup. So taking that approach and blending it with the defense contracting is really kind of brings to focus the issue of trust in autonomous systems. And it was actually fundamentally a first principles problem that we're dealing with. It was, how do we have these hyper complex systems that are in the defense world often asked to do potentially lethal type activities. So how do we create a system that will actually allow to use? And so that's what we're going to address today. And we went back to a first principles approach, and that's what we're going to cover as we go through. So Project FIDES, Frameworks for Integrated Design of Entrusted Systems, fundamentally went to look at the driving indicators of what it really meant to even trust a system. And one of the biggest problems that we came across is that trust is mostly a human-to-human situation, and it breaks down very quickly when we talk about systems. We don't have the same behavior towards systems. For instance, with humans, we have forgiveness. With systems, we don't. We can have hundreds of thousands of car crashes every year that don't make the news, but the one that is an autonomous car makes the news and is broadcast everywhere, for instance. So one of the things that we're trying to understand is how to break down and understand the design space so that we can ensure we're putting together entrusted systems. So the first thing we want to start with is a fundamental recognition of how autonomy kind of actually realizes itself in engineering design, specifically around autonomous systems. And one of the challenges is you end up having too many buzzwords out there between AI, between autonomy, between MUM-T, man-to-man teaming, and all these other things. So we found that a simple heuristic was autonomy is a gradient capability that enables the separation of human involvement from systems performance. And as that enabler, it actually falls on 3 dimensions. The first dimension is truly what we consider autonomy, the independence of the system. Is the human in the loop, on the loop, or off the loop? The second dimension is intelligence. Is it deterministic, non-deterministic type programming? You hear about that colloquially, we'll call that AI. And then the third dimension is that MUM-T perspective of that system collaboration. Now, the uniqueness of this model, this simple heuristic, is that I can map both humans and machines on the same system. I can show you the difference between a lowly private in the military versus a special forces operator versus a satellite versus a ground vehicle. And it really captures the essence of what we're talking about with autonomy. And the 3 dimensions are important because this is how we build out the frameworks for designing or creating entrusted systems. So fundamentally, the overview is trying to figure out what the customer, what the user is asking the system to do, where they're asking it to perform it, the environment, and then the trust framework really looks at what will you allow it to do. And what we were finding is we'd have these great ideas from the customers of what they wanted it to do, but then the environment of where they wanted it to happen, like for instance, blue sky, daytime air flight, is a whole lot less complicated than nighttime all-weather ground navigation. And so as a complexity function would then really start violating a lot of the things that they'd actually allow it to do. So moving forward, the environmental framework, the full sole function of this is to establish complexity. What are you asking the system to do against where you're asking it to perform it? And we fundamentally say, hey, if you capture physical, you capture operational, you capture information activities, you're going to kind of hit the nail on the head for the major themes. The cool thing about this framework is that as long as you're measuring it against independence and intelligence, you can use any framework you want, from a simple single factor to as something as complex as the JP5-0 with almost virtually 1 to n sort of functions that go with that. The key is that what you'll find from the environmental impact is it will tell you the minimum levels of independence and intelligence required. It's not intended to be discrete or prescriptive. It's intended to start capturing assumptions that you can challenge those assumptions and begin to negotiate them as well. But again, fundamentally, it's intended to focus on the minimum levels of intelligence and independence required to achieve the system's performance. The trust framework, this was honestly probably one of the most difficult ones we had to deal with because trust is turtles all the way down. And the problem with trust, as mentioned, is it's human to human. And so we went through a bunch of different permutations and we fell upon the word that factors better. It's entrusted. You entrust a system to perform a task because it's the baseline starting point. Trust is really challenging to pin down. So hence frameworks for design of entrusted systems. So what will you allow the system to do? And we felt fundamentally, to keep it simple, this was a function of ethics, because we always talk about ethical AI, ethical autonomy, ethical this, ethical that. But ethics is a little messy too, because there's rules and then there's cultural applications, like the Society Against Killer Robots may contest the development of a system that by rules are or is allowed. And so understanding, and this is really fundamentally capturing the stakeholder perspectives, what is the ethical considerations, rules, and cultural implications of your design for trust? The second one, which is really critically important, something that we found was typically not addressed soon enough into the design cycle, was assurance. We like to put non-deterministic programming in, and then we find out we can't V and V it. So V and V becomes one of the most important aspects. Can you actually perform verification and validation on it the way we'd like, or the way that will be acceptable or trusted? And then safety and security are two scalar functions that say how important it is for the ethics and for the assurance as it goes forward. So we measure these along a gradient here. So, is there cultural resistance? Are there rules that prohibit it? And it's not intending to tell you where to go get it. It's intending for you to ask the question for you to go capture the information that's critical to your process. V and V basically says here, pretty simply, is it verifiable? Is it deterministic versus is it unverifiable and highly undeterministic? Then safety and security are scaling functions. We try to base this off of MIL standards. So, is it catastrophic? Is it not catastrophic? Is it a Roomba? Is it a warhead? And then security, we've focused on, in this case, Lockheed Martin cybersecurity resiliency levels, which capture a lot of the information applications that go in it. So can you actually secure physically and informationally and in the network, the system in that sense? So just a quick comparison here, the difference on this scale between like a unmanned aerial vehicle and whether it's just a recon or whether it has lethal implications can shift this back and forth on these scales pretty quickly. Because what trust tells you is the maximum intelligence and independence you'll allow the system to have. And again, just like the environmental framework, it's not here to be discrete or prescriptive, but to capture those assumptions. Because you then put them together into the reconciliation. Do I have an overlap that identifies an entrusted design space? Or are the requirements in the environment too complex for what I will allow it to do? Doesn't mean that the design is impossible, because that third dimension that we talked about earlier, if I don't have that design space, perhaps I can split it up across the systems of systems. And this is one of the biggest frustrations we've always had, is think of like a self-driving car. A self-driving car by nature is going to be more complex because it's encapsulated in the entity called car. But if I could break into the systems of systems called road, and I could start having intersections identify themselves, self-queuing mechanisms, road signs, speed limits, everything else was identifying to the car, that car by default would be able to be less complex because the road system is taking on a lot of that weight. The same thing happens within manned-unmanned teaming, or especially in the aerospace and defense industry when we talk about systems on the battlefield. For instance, just because I won't trust a non-deterministic AI-enabled route planning software doesn't mean I can't actually use it. I just won't trust it to be completely independent. So I can have that high intelligence and then factor it over to be less independent, human in the loop. It comes up with a series of plans. A human operator selects the best plan. We can then hand that off to a middling quarterback that has, maybe some more playbook planning, more independent, less intelligent. And then the final, that lethal activity here, can be very unintelligent and very independent, but it's not making the decisions. And so by doing the systems of systems progress, we can actually achieve an entrusted systems of systems that meets the customer requirements in the environment without violating trust. So what basically the simple flow on this one is we take those requirements, we run them through the raw scores, we normalize them, pop them through a pretty simple algorithm, which we'll talk about in a second. It comes up with a visual design space. It's just a quick way for architects, requirements managers, program managers, customers to reconcile the design space. I'm not going to go into too much of the math right here, but fundamentally, as it works, is that trust independence is a function of the safety and security as scalars to culture and rules. Intelligence is safety and security against verification and validation. And then environmental independence is a function of those complexities that we measured in the environmental framework. And so one of the notes on here is that you can do this with n factors. This can just be generalized so that you can add it in. We created a pretty simple little tool here where you can add different weights, and we can also weight the importance of one value over another. So then it ends up working out pretty well to do that requirements deconfliction, to do the systems trades, and to really fundamentally at the beginning ensure that you can create an entrusted system. So at this point in time, I will cede my time and will answer questions at the Q&A at the end of this session.
Let's go back to San Jose to see if there are questions from there.
Hi, I believe we don't have any questions currently.
So let's see what...
Michael, thank you for a very enlightening presentation. I think it inspires a lot of questioning here, and I don't know how much you can actually express. We have fundamentally, I know Mark is here, and the question comes up is how much of this technology is available for commercial use, and also in terms of from the governmental perspective, from a NASA perspective, how much of this technology is available for usage? Over.
Great question on that one. So fundamentally, the framework is open for use. It's the ability to start and analyze any technology. So it's a framework to really understand, again, the complexity and the risk associated with your design functions. So when we're talking about, like the previous presenter was talking about the different the chipsets and the different protocols that could be done on them and everything else, the question that comes out is those are really cool. How do I apply that into an actual usable system with the humans? And again, balancing ethics and assurance to establish that entrusted design space is kind of one of the bigger hurdles we have. We have a lot of technology out there. So how do we apply it so that the users will actually accept it? And that's what these frameworks attempt to answer.
Michael, I have a second and final question. In the context of design space exploration, and of course, within your activities, a lot of analyzing a lot of flight data, and to what extent knowledge captured from flight, real flight information, gets implemented into this framework to improve further forecasts and predictions. Over.
Great question. So some of that, I will say that the model had its own verification validation done on some of our real world entities at Lockheed. What I can't go into is some of the details on that, but what fundamentally it does is, again, going back, it's taking those requirements and negotiating them sooner. So the flight data goes into the environmental framework. So what sort of environmental considerations are we actually dealing with? Now, if you're not establishing the entrusted design space off the bat with the level of granularity that you have, you can then enter into the discussion with your flight data to say, hey, we believe it's super complicated or complex. However, with the flight data, we're able to actually negotiate out because we have a better understanding of what we're looking at. So that's one of the things that it drives, is bringing the data to the conversation, but putting and documenting all those assumptions going in before you get too far in the design phase and you realize we really need a lot of data to get in here. And that can be one of your risk reduction strategies, is we know we don't know enough about this. So we know that early in the design phase, we're going to need to go get a lot more data than we currently have to try to work into that entrusted design space.
Thank you, Michael. Thank you very much.
Thank you.
So the next question that our next speaker is going to answer is the following. Is AI well suited to the limitation of deep space communications as well as to support satellite operational and communication infrastructures?
Hello, my name is Carter Edmond. I am a senior computer science student here at San Jose State University, and I have the pleasure of introducing Professor Andrew J. Hacker. Professor Hacker is founder of Thought AI, a novel artificial intelligence platform leveraging patented self-aware information, complex adaptive systems, and blockchain. Thought AI's mission is to make all digital information self-aware using a bottom-up approach to enrich data and increase value for companies and organizations that depend on information insight. Collections of bits resemble digital neurons or a hive of digital honeybees to produce powerful AI/ML algorithms that learn and have memory. Professor Hacker is also cybersecurity expert in residence at Harrisburg University, where he is helping to further the university's position as a recognized world-class institution in cybersecurity. Mr. Hacker is the former Deputy Chief Information Security Officer for the Commonwealth of Pennsylvania, where he implemented and improved cybersecurity programs statewide, created enterprise security strategies, standards, and policies, enhanced overall application security, and was responsible for risk management and compliance across the Commonwealth. Mr. Hacker has publications in Network World, Information Week, HelpNet Security, and appears regularly as cybersecurity expert on Fox, NBC, and CBS News affiliates locally and nationally. He has the following certifications: CISSP, ISSAP, PCI, QSA formerly, CTGA, and CGCIO. Please join me in providing a warm welcome for Professor Andrew J. Hacker.
Hello, everybody. My name is Andrew Hacker. Thank you for that very warm introduction. I am the cybersecurity expert at residence at Harrisburg University, and I am also the founder and CEO of Thought AI. We are leveraging intelligent agents for all of the data problems that we see out there, and I will make the case for intelligent agent artificial intelligence in space applications. So let's start by looking at some of the challenges for artificial intelligence in space-based applications. It's well known that data volume is increasing significantly across the globe in all kinds of information technology applications. There are so many more sensors, Internet of Things, autonomous vehicles, our phones, all of the things that produce all of this information. And certainly in satellite applications and in space, improved sensor resolutions, create much more increased volume in the data that's produced. And we all know that satellites have limited computational power, due to the weights that are needed to launch satellites into space. We need to reduce those weights and thereby keep compute power lower. There's also limited communication bandwidth, both intra-satellite and also between satellite and Earth stations. And also cybersecurity and resilience is a very large issue. Sensors that read information need to be secured and resilient and need to be protected against tampering. Another thing that's happening generally in space and also, in all of the information systems that we have is the complexity increases significantly as all of these inputs and all of this data become more complex and increase greatly. Another issue and another challenge is round trip time. Between satellites communicating to Earth-based stations, there is latency for those communications. So responsiveness becomes a big issue. When we talk about machine learning and artificial intelligence, the traditional, and I will use the word traditional to describe how data is processed today, is that we have artificial intelligence models that basically require training. They require massive amounts of data to be trained. And once they are trained, we measure their effectiveness, but essentially those models become locked. And once those models are locked, they are only really effective for the data that they are trained on. Once that data winds up changing, or if the types of information that model was trained on initially do change, if those conditions change, the performance of that particular artificial intelligence model may decrease over time. So the ability for an artificial intelligence or machine learning model to adapt as the data or the constraints or the characteristics of the system change over time is extremely important. So what are intelligent agents? We might have heard this term used before. When we think of machine learning models, we think of deep neural networks, and essentially deep neural networks are, connections that are produced inside the model that allow that model to recognize patterns, right? So if we take, training data that consists of certain patterns that we want this machine learning model to look for, essentially all of the layers within that deep neural network are changing their weights and changing their connectivity in between the nodes on that model to essentially allow that model to recognize certain patterns. So the whole idea of an intelligent agent, intelligent agents have been around for a long time, probably 20, 30 years ago. IBM was pretty big in creating these agents and creating systems around that. And I think the basic idea was that computational power back 20, 30 years ago was not necessarily sufficient to calculate all of the different computational requirements that intelligent agents required. So an intelligent agent is essentially a self-contained unit that contains the ability to process information and realize goals, within that contained agent. So the agent actually has certain abilities. It basically looks at its environment, and based on its internal rule sets, it makes judgments and can commit actions based on what it sees in the environment. So an agent can basically contain lots of different capabilities. It can store prior knowledge. It can have application code that actually gives it specific goals, certain things to look for, certain optimizations to either increase or decrease. But it looks basically at the observations that come in from the environment. And these are, could be anything from, the speed of a car. It could be certain conditions about the roadway. In satellites, observations can be, basically image data from the sensors on that satellite. It could be trajectory information on how that satellite is moving, through geo orbit. And based on the environment that it sees, the agent has very specific rules that say, if I see X, Y, Z, then do action A. If I see a different set of conditions, then do action B. And once it does these actions, the environment can presumably change based on that particular agent's actions, and it can adjust its internal logic and adjust its action space based on how that environment changes based on its own action. So we do say that agents have a certain level of autonomy. And the other thing I want to point out about intelligent agents is they can be as simple or as complex as the designer of that agent requires for its particular use case. So we can have agents that are very simple. We can have agents that are simply coming from a particular sensor and say, if that sensor has certain values, then assign, this particular label to that sensor data. If it has a different set of sensor data, we can allow it to label with some other kind of characteristics. We also have a lot more extremely complex agents that can have very complex embedded goal sets. We can have what's known as the actor critic, where the agent does the actions, but there's also another component to that agent that has a critic that says, how do these actions correlate with the goal sets that I have? Did this action lead to a positive result based on the requirements that I have? If the answer is yes, then reinforce that action and make it more likely to enable that action in the future. If the critic says, well, no, this didn't help me achieve my goal, we can actually reduce the strength of that action so that the agent knows that in the future, it would be less likely to create this action. This is known as reinforcement learning, okay? And we can also look at things like the actual performance of the agent itself. So moving on to the next slide. With Thought AI, the original idea behind our platform was to basically make all information smart. If we think of the current paradigm today, generally we think of applications, and applications can be a word processor, it could be an Excel spreadsheet, it could be a complex operational system application, or it could be an artificial intelligence or a machine learning model. And additionally, all of applications essentially process data, right? And in the current paradigm, data essentially right now is not smart. One of the easiest analogies to think of is the difference between animate and inanimate objects. If you think of an inanimate object like a rock, versus something that is an animate object, say an ant or a honeybee or something like that. A honeybee actually has its own agency. It has its own thought processes. It can take information from its environment. It can make decisions based on that. And if we think of today's data is more like the rock. Okay. I mean, a rock can't do anything unless there's something external to it that is acting upon it. So if we have a rock that's on the top of a hill, it can roll down to the center of that hill only from the force of gravity. It can't really do anything other than basically obey the rules of external forces. But if we have something like a honeybee or an actual agent with its own autonomy, it can actually make its own decisions and make its own actions. So what we've basically done is we take every piece of information, whether that's a piece of data, a piece of sensor data, a pixel in an image that's collected, or an action, or any complex set of goals, and we basically encapsulate that into small containers. And each container is protected. It's encrypted, so it has an outer shell. If you think of how cells in your body, they have a protective membrane, right, that allows information to pass into it and to pass out of it. But essentially, it's a self-contained unit. And what we do is basically take all of that data, all of that information, encapsulate it into these small intelligent agents. And we also give it the ability for that information to travel, both in physical space and also informational space. So we can think of individual agents that might contain, pieces of data from a certain satellite imagery layer, right? And we could have multiple imagery layers. We can also have operational and telemetry type information. And each one of those pieces of data is encapsulated in its own agent. And certainly we can have some agents that have lower complexity, that do simple things that are easily calculable. We can have more complex agents, and we can also have a hierarchy of all of these agents so that they can actually interact with each other, form connectivity with each other, have a memory of other agents that they've encountered. And each of these agents still has embedded optional, or I should say operational goals that they can augment and increase. So when we combine all of these different things, the connectivity that we see in neural networks that allows pattern recognition, the sort of the autonomy and the agency of particular intelligent agents with rewards and goal sets, and every piece of data that is present on a system, when we combine them all together, we sort of get this ability for these intelligent data agents to essentially converge on solutions. So if you could play that video for me, that would be great. Now, let's just see how until this starts up. Great. So this video is essentially a small application that runs a complex adaptive system and a bio-inspired algorithm called particle swarm optimization. And these are very simple rules. So each one of those dots represents a particular agent with rules that basically say decrease the amount of space between yourself and that goal, the goal dot, right? So that dot that's being pressed is essentially, a point on that screen. And each one of those agents, by looking at it, I think they designed it for about 300 particular agents. They pretty quickly, with some very simple rules that basically use gradient descent to say, I want to decrease the amount of space in between myself and that dot. And you can see even autonomously, they kind of pick up this swarming behavior. So if you can think of all the information created and ingested into these particular agents, with each agent maybe only having a very simple rule set, we can see that there is this emergent property of extremely fast and extremely efficient optimization around that particular goal set. So moving on. Trying to advance my slide here. Okay. So the benefits of doing things this way, the benefits of treating all information as an intelligent agent, even though there might be slight amount of overhead relative to basically processing data in its raw format, this added amount of overhead is a functionality that we can see from these intelligent agents. What it also gives us is a set of universal data, right? So if we have data that's ingested intelligent agents, we can kind of process that once, turn that piece of data into an agent, and then we can leverage that agent in many, many, many different use cases. So it's sort of a process once, use many type of thing. Not only that, but data that is collected or ingested in one particular area is equally applicable to lots of different particular use cases. So could be cross-industry. We could have something where we find, a piece of information that might be value in one particular data set. And then the knowledge and the value of the information that's created in that particular data set is transferable and usable in other different types of use cases, applications, and industries. And not only that, but this applies also to the actions that they create. So if we have an intelligent agent that has a set of actions that is pruned and improved and optimized over, many, many, many different repetitive steps, that there is value in that particular agent. So the insight that agent gathers in its particular environment is also transferable, and that intelligence is transferable. Processing data with intelligent agents also unlocks the value in the data. Most companies, most industries, most use cases, barely scratch the surface of realizing all of the value in the data that they process. Companies are lucky if they can actually realize maybe 5 or 10% of the value in all of their data. In a lot of cases, the data flow and the data volume happens so fast that companies, algorithms, and platforms literally wind up throwing away data because they can't process it fast enough. The other thing that processing data with intelligent agents gives us is the ability to monetize actions. We can monetize actions, we can monetize data down to very specific and discrete levels. And successful models kind of retain their identity. So it's not just we have a model, sitting on some cloud computer somewhere. That model is actually usable and transferable and can actually actively look for other places where it can be useful. There's also an extreme increase in adaptability and responsiveness. So intelligent agents, they can basically they can change their own internal logic. So that's another important thing. And that's part of the intellectual property that we have, is that when you have an agent that can sense its environment, it has internal code that evaluates the actions that intelligent agent takes. We can also adjust certain parameters within that agent based on the external environment. And this is, much the way the human brain works. If we touch a hot pan on a stove, our reflex pulls our finger away, and our brain says, oh yeah, let's not do that again, right? So it actually learns. So we have intelligent agents that, as they, process through data and process through their actions, they are actually learning. They have memory. They can look at their history, and based on that, they can make future decisions. There's a very strong case for a reduction in cost, because as I said before, since we're ingesting data into these intelligent agents, we're sort of processing once. We're labeling data, we're giving it provenance. The agent actually understands or has a history of where it was created, what the device it was created from was, what were the conditions under which a particular piece of data was created. And all of this metadata and all of this information is self-contained within that particular agent. So at some point in the future, some other application could go back and query that agent and say, give me some information about this particular environment where you did this particular thing. It also leads very strongly to explainable AI, which has been a big challenge for artificial intelligence, where you've got models that are trained And in some cases, artificial intelligence systems are so complicated that even the designers don't really necessarily understand how certain answers came about based on how the machine learning algorithm is trained. So intelligent agents can actually literally tell you why they made the decisions they made, the path that they took through a certain set of conditions. So this leads to much more explainable and useful artificial intelligence. And as I said, since every intelligent agent has its own encryption, they're individually encrypted. And that's another thing, since we leverage blockchain for private key management. There is no sense of, if I basically steal one key, I have access to all data, because every intelligent agent has its own individual encryption. So, and I also mentioned too before, there is a slight amount of overhead. So if we think about the overhead as being maybe 5 to 10%, depending on the particular application of this agent, right? That overhead is significantly small compared to all of the exponential level of functionality that we have from this data. So if you think about, maybe we've got 20 different data points that individually would take up storage space, would take up communication bandwidth. But if we can have one agent that is actually responsible for those 10 data elements, that agent can represent information about those individual data pieces. So in essence, the slight a bit of overhead in that particular agent gives us much deeper added functionality and information about those 10 different elements that it's responsible for. Intelligent agents as a service. So the Thought AI platform is essentially several abstraction layers that allow us to basically create all kinds of use cases using intelligent agents. So when using our platform, companies and organizations will basically build agent-based models. So, using basic drag and drop, low code type interface, we can actually design models that contain data sources, that contain the types of information that we'd like to see from those particular data sources, how those data sources are processed, and how intelligent agents will actually execute and what types of information they will return. We can connect space-related models to non-space industries. Since we are, using these universal agents, the information that they collect, from satellite imagery can be processed and distributed out to many different industries with minimal effort to get that type of information. All data is inherently secure on the platform. All agents are completely encrypted, so once data is ingested onto the platform, that information remains encrypted. It's a different approach than sort of zero trust encryption and homomorphic encryption. Homomorphic encryption is, being able to work with encrypted models and perform functions on information while it's encrypted. In our case, since agents sort of control access to the information that they have, we can have a case where a particular information can be queried and can give the entity or the service that's querying that information some knowledge about the data without actually revealing the data itself. And as we've seen, intelligent agents actually converge faster on solutions in complex environments. In fact, the whole science of complex adaptive systems and the ability to manage, high volumes of different types of unsolvable variables, complex adaptive systems are very much more efficient than just sort of straight application and business logic. And we can think of how this works by looking at bio-inspired, or their so-called nature-inspired algorithms. So these are algorithms that use agents and model basically the way nature does things. There are algorithms for the way birds flock, the way fish swim in the sea, the way honeybees actually go out and collect information about food sources. Once one bee finds a food source, it goes back to the hive and it communicates the location of that food source to the rest of the hive. that leads to more efficiency in how that hive actually collects food. Even ants and the way they crawl and leave pheromones, they communicate to other agents. And in fact, there's lots of research that shows that the so-called ant colony optimization algorithm can actually solve the traveling salesman problem in a fraction of the steps that it takes to brute force the solution for that. So the other idea too is that typically in your traditional AI and data model, the data itself is static. It doesn't move, certainly doesn't do anything unless some external application acts upon it. And the applications themselves, they're stationary, right? They sit on a cloud computer or a cluster or a satellite, but they don't move. The other thing that intelligent agents can do is, since they contain application logic and they contain artificial intelligence logic within their container, they can actually travel not only in informational space to find optimal solutions, but also in physical space. So an agent can literally be created on the ground, be transmitted to a particular satellite, could move from one satellite to another satellite, seek out the conditions that optimize its goals, and when it's done, it can return back to its place of origin. So this whole idea of mobility is an extremely important thing in our space. Just to give you an idea of what this looks like, so as I mentioned before, we do use blockchain to control how these agents operate. We need to ensure that the agents do what we have designed them to do. Agents, can go out and interact with their environment, and then they report back to basically the blockchain management system and say, yep, I did this particular action, here was the result, and here is a record, of that particular action that I took. So you can kind of see, we actually call our agents internally, we call them nuances. An idea of how our fabric works is you can see how a nuance gets generated along its basic model. It can go out, it can read a sensor, and it can travel in physical space to do this. It can actually send an alert, it can activate some switch, but then it also keeps a record of what it's done. So here are some design specifications of how these agents work and interact with blockchain. We publish services on the blockchain. Intelligent agent gets created. It goes about collecting data, running its internal models to create the value that the designer created, and basically communicate with various systems as it goes along these goals. We also have some instances where we can see there's also a hierarchy to how these agents work. So we might have so-called low-level agents that are basically agents that ingest certain pieces of data. They have very simple rules, very simple analytics. And then we might have a higher level agent that basically connects to the lower level agents with a higher level goal set. So you can think of almost infinite levels of hierarchy with how these agents work and the different types of goal sets that they have. And just finally, before I wrap up, I'll mention a little bit about the intellectual property that we have. We do have a patent that was issued in 2016 for these particular agents. So these agents are encrypted. They're a container. They're basically the extension of a particular containerization platform all the way down to the data level. So when we say that we're building machine learning and artificial intelligence from the ground up, we literally are. We're starting with the smallest pieces of information, giving that piece of information intelligence, allowing it to interact with other similar types of information along a goal set. And as it basically discovers and finds these value solutions that optimize along its goal sets, it can present that to different layers. We always like to say that traditional AI and big data analytics is always looking for the needle in the haystack. Well, in our cases, we actually have the agents that understand, realize that they are in fact the needle, and can present that up to the applications that require it. Okay, so I'll end there. Thank you very much. I appreciate the opportunity to present for you today.
Next, ladies and gentlemen, further perspectives on artificial intelligence and machine learning. So we continue on these similar themes. Question issue that you will now hear more about is how it is that advances in computational sciences can transform small spacecraft from remote instruments from Earth to capable, smart agents that autonomously accomplish missions. Please join us for this next session and discussion. Thank you.
Dr. Lowry serves as NASA's chief scientist for reliable software engineering. He became interested in neuromorphic computing as a means of radically improving compute power and energy efficiency for NASA's embedded aerospace missions. In 2019, he was awarded project funding by the Science Technology Mission Directorate Game-Changing Technology Division to work in the area of radiation-tolerant neuromorphic computing to close the gap between terrestrial neuromorphic computing capabilities and embedded space computing. Lowry has been principal investigator on advanced software engineering technologies through NASA Aeronautics and space R&D programs since 1996. The major theme of his research has been the automation of mathematically based methods for software engineering, including generation and verification of NASA aerospace software systems. During Project Constellation, he led the definition of the Lunar Surface Systems software architecture. He led human space research for development of advanced software verification tools, including from 2006 through 2012, the maturation of the software development tool chain on Project Orion, NASA's multi-purpose crew vehicle. Dr. Lowry managed the NASA Ames software analysis of the Toyota unintended acceleration at the request of the NTSB in 2010. From 2012 to 2014, he served as chief scientist for DARPA's META project, which emphasized automated design tools and formal verification for cyber-physical systems, such as next-generation ground vehicles. Dr. Lowry awarded a NASA Aeronautics project in 2016 to determine the feasibility of an autonomous operating system for UAVs. AOS integrates artificial intelligence reasoning engines with a widely used NASA middleware platform called Core Flight System to provide an infrastructure for smart UAVs. Dr. Lowry and his team prototyped putting the training and procedural knowledge of an airplane pilot into AOS towards pilot in a box. Dr. Lowry received his MS NVS from MIT and his PhD in 1989 from Stanford University in artificial intelligence. Dr. Lowry is an IEEE Automated Software Engineering Fellow with numerous publications. He serves on the following journal editorial boards: Springer Journal of Automated Software Engineering, ACM Transactions on Intelligent Systems and Technology, and Innovations in Systems and Software Engineering Journal. Without further ado, Dr. Michael Lowry.
This is Michael Lowry. Do you hear me? Oh, fantastic. Okay, please put up the slides. Okay, I'm going to talk to you about a project that actually represents a number of people. It's called Neuromorphic for Space Autonomy. It includes at NASA Ames, Johan Schumann, Eric Barwitz, Kirthina Kathana, and also the flight team under Marcus Murbach, and of course the intern that you just saw. And then at Glenn Research Center, Jeanette Briones, and of course a special shout out to the folks at Intel in the Intel Neuromorphic research community. And you have other speakers, Tarek Taha, and Garrick Orchard, and of course Marcus today. So let's talk about Neuromorphic for Space Autonomy and why it could be revolutionary. Let's go to the next slide, please. So what is neuromorphic computing? It means mapping neuroscience to silicon. This is coined by Carver Mead in 1990, who also wrote the textbook on VLSI design in 1980. The key thing to remember for this talk is that neuromorphic processors have outstanding power efficiency, 100 to 1,000 times the throughput per watt compared to CPU, which is especially important when you talk about these small satellites, these 3U6 satellites, 10 centimeters by 10 centimeters by 30 centimeters, that are kind of restricted to 10 watts to 20 watts. So that power efficiency is actually enabling. And that enables us to put artificial intelligence, machine learning applications at the extreme edge of space. They can be used by themselves for smart instruments and small nanosats in conjunction with command data handling computers, and also as force multipliers used in GPUs. So as I said, it means mapping neuroscience onto silicon. The human brain is incredible. Exascale computing at 20 watts. 86 billion neurons, 150 trillion synapses, all working in synchrony. And then in starting roughly 2012, Carver-Mead's vision actually started being realized. You saw in 2012 the Google TensorFlow processing unit that provides 83 times the power efficiency of a CPU. And actually you can buy one now in a Google Pixel smartphone. Of special importance, and the one that's up in orbit, is the Intel AIIA. It incorporates onboard learning and also does a much finer grained emulation of neurons with spiking neural net hardware. And then analog computing, for example, a small business by the name of Mentium has produced a analog neuromorphic processor, and that achieves yet another factor of 10 improvement in power efficiency over digital neuromorphic. And all these combined are going to enable us to take the mission control, which is on Earth, and then be able to upload it to orbit and be able to have intelligent small satellites that are going to first help us with Earth's observations and a myriad of work, including communications for humankind on Earth, and then with radiation and fault tolerance, be able to extend our reach into the solar system. Next slide, please. Okay, the mathematics is basically vector operations. I'll point out that one of the most popular programming languages is called TensorFlow, tensors being the generalization of vector algebra to tensors that was developed by Einstein for purposes of describing general relativity. And so 3 types of vector operations to keep in mind. One of them is deep inferences, and you represent the activations of a previous neural layer or the input to your senses. There on the left, you've got a column vector. It goes through matrices, which represent the synaptic elements. They produce these row vectors after being thresholded. That is an important operation, but not from the viewpoint of the energy. And then that goes through multiple layers. So we're all familiar with this kind of deep inference. You're also probably familiar with deep learning, where you take the difference between the classification that comes as an output of after you do the forward inference, and there is an error, you propagate that error using the chaining rule back through the neural nets and make adjustments to the synapses. What seems to be most likely for actual neural systems is what's called Hebbian learning, where you take the outer product of the presynaptic neurons and the postsynaptic neurons, and those become a weighted update to the synaptic matrices. And that actually seems to be what's happening, at least in the cerebrum. So, and this is a local learning rule, and chips like Loihi actually support that efficiently, as opposed to the deep learning, which usually requires a GPU cluster in order to achieve that kind of back chaining of the output errors. So that's the mathematics in a nutshell for neural computing. Next slide, please. Now, here's why you have incredible power efficiency for neuromorphic computing. Let's take a look there at the diagram on the left. This actually represents the majority of the neurons and the synapses in the human brain. And you see that you have parallel fibers there in the upper left, and then Purkinje cells that make synaptic connections onto the parallel fibers, sum them up, and then if they reach a certain threshold on summation, they'll fire. Now, this particular type of biological neural net is most representative of what you see in the cerebellum. Similar ones, though, of course, also are in the cerebrum, the cerebral cortex. Now, with neuromorphic, meaning mapping onto silicon, you map this onto an analog crossbar array represented here on the right, and you see voltages representing the presynaptic neurons, and each of the synapses is represented by conductance. And then what you do is you get a dot product of the conductances with the neural activations. Those are summed up, and that produces a current, which is then converted in an analog to digital converter into the value for the postsynaptic neuron. Here's the thing. With this kind of analog crossbar array, each of those variable conductances can be realized in a number of devices, such as the flash transistors, which are on your SD cards or in your computer memory. I have 2 trillion NAND flash in my Mac Pro computer. That's 2 trillion synapses, not the 1500 that's in the human brain. But in one clock cycle, you've done all the computation for a neural layer. And if you try to emulate this on a CPU or a GPU, in that one clock cycle, you are still trying to do that first multiply of one of these, as opposed to all of these synapses being able to do that multiplication and the summation in that one clock cycle. That's why you get this incredible power efficiency for neuromorphic computing. Slightly less if you do it digitally. And the implications for space are incredible. Let's go to the next slide. Okay, so let's consider the International Space Station. It took 11 years, tens of billions of dollars, and in 2017, the solar array provided 100 kilowatts of power. This has been recently upgraded to twice the amount of power. And that's the picture of the International Space Station. The picture below that on the left is an astronaut who is repairing one of the MDMs, multiplexer demultiplexers, which is command and data handling for the International Space Station. Some of them are on the outside of the space station, some of them are on the inside. For the outside, they actually have to do a spacewalk in order to replace that. Levels of hierarchy on the International Space Station MDMs, and each of them is actually bigger than a 3U CubeSat because their heritage is a 386 computer, recently upgraded to Pentium computers, and they're fault tolerant through triple redundancy. You can't actually buy these types of Pentiums anymore. We have to scour them for various sources. And so for 100 kilowatts, you get this MDM array. In 2017, NASA Ames put up an enterprise server to do payload processing on the International Space Station. That took 1 kilowatt of power. And with that 1 kilowatt of power, we get 1 teraops of processing. In contrast, 1 watt of processing, 1,000 times less, with an analog processing that I showed you in the last slide, gives you 10 to 30 teraops. So contrast the 1 teraop through 1 kilowatt with the 10 to 30 teraops for 1 watt. And you can start seeing the implications. With Marcus Murbach and the team I just talked about, 2022, after 1 year of effort, less than $1 million, actually more on the order of 100,000, we put up test 13, which basically provides 10 watts continuous power, and we flew as a technology and demonstration the Intel Loihi processor. Next slide, please. Next slide, please. Okay, and so what that's going to get us is we're on a roadmap to get sentient small spacecraft. Today's small spacecraft are typically single point sensors, very bandwidth limited, and there's minimal onboard processing. The onboard processing is very limited by size and power, and either you're typically doing single spacecraft missions or non-coordinate constellations, and we're pretty much restricted to a LEO because of fault tolerance and radiation. The next generation of small spacecraft are going to be high throughput, low power on board. So we're looking for teraops per watt of power, enables sentient action and data processing, compressed communication to Earth, and high information content. In other words, the data is processed on board instead of being sent to Earth, and opportunistic science. And we want to be able to go from low Earth orbit to widespread solar system exploration. Next slide, please. And then in the other configuration, where we have CPU and GPU on board, we're going to achieve a force multiplier through heterogeneous computing. And the 100 to 1000x power efficiency that we get through neural computing combines with CPUs and GPUs. And in this example, which comes from Tesla, but you also have similar ones in other instantiations, you get roughly a 20-fold improvement in your throughput per watt by incorporating neural processing. So it's very heterogeneous computing has a lot to offer. Some limitations for neural computing are made up with by incorporating a CPU and a GPU, but you get the heavy lifting, at least in terms of arithmetic and vector processing, done by your neural computing. Next slide, please. Okay, so in less than 1 year of effort, on the order of $100,000, we launched Test 13 into orbit in January 2022. Here on the left of the slide, you see a part of the preparation for testing for before it goes onto the launch vehicle. You see how small it is. It was launched on a Virgin orbit, which is a Cosmic Girl is converted 747, and then Launcher 1 drops from the 747 kind of as a second stage, goes up into orbit, and Test 13 was actually the first CubeSat that was released in the launch from the Virgin orbit. And so it's been up there roughly 6 months. If we go to the next slide, we'll see what the orbit looks like. So this is an orbit where we've done 16 experiments to date. Experiment 12 encompassed one orbit, and you see the yellow is the sunlit portion, the black is at nighttime, and it passed through the South Atlantic anomaly. The South Atlantic anomaly is basically where part of the Earth's magnetosphere comes down low, down here to 500 kilometers, and what's happening there, you get high exposure to radiation. So other parts of low Earth orbit are relatively benign, and I'll quantify this in the next slide, but it does point to the fact that we need to be able to deal with radiation tolerance in order to get to the beyond low Earth orbit, the solar system. So let's take a look here on the right. What we get here is the memory upsets on board the International Space Station. These correlate directly with the radiation levels that are experienced in low Earth orbit. You see here on the left, at sea level, you get about 0.1 proton flux per centimeter squared per second. As you go up to the orbit of the International Space Station, you get a 100-fold radiation increase. But then as you go through the South Atlantic anomaly, that goes up by another factor of 10 to the fourth or 10,000. So the South Atlantic anomaly actually is representative of what you see out in deep space. Lunar orbit, go back one slide, please. No, one slide forward. And, yes, and so then a solar flare gives you another factor of 100 beyond that. So now we're talking in excess of 1 million times the proton flux that you see at sea level when you get a solar flare that's not shielded by Earth's atmosphere and the magnetosphere. And it shows up in a number of effects on the electronics. Over time, the total integrated dose accumulates, and most commercial devices fail at about 30 kRad. And then you also get single event effects, where you get a bit flip. And the way that most computing is done nowadays, particularly with conventional software, conventional hardware, one bit flip will cause the whole computer to crash. So we need to mitigate both the total integrated dose and also those bit flips that can be catastrophic and need to reboot for your conventional CPUs and GPUs. Next slide, please. So we've been just an example of a solar flare. One occurred actually in April 17th, 2022. The terrestrial impact, as you can see in the lower left diagram, was focused on Asia and Australia. This is kind of what it looks like, a solar coronal ejection mass there just above that. And we saw a very high spike in proton fluxes and also in heavy ion fluxes. How can you mitigate that if you're doing neural computing? Well, one way to do that is through redundancy. So here we have some experiments that were conducted with Loihi on the ground, where we had two spiking neural net networks. They were both producing similar computations. In this case, they were actually trying to decode images of numerals. There's actually a very slight difference because we injected the equivalent of what happens when protons impact the Loihi chip. That's on the lower one here. And although you can't see it with your naked eye, you can pick that up with parts of the Loihi processor that are actually comparing the differences between the two spiking neural networks, and then you get a different signal. That can tell you that you're experiencing radiation and you have to invoke fault tolerance protocols. So at the level of firmware, we've been able to show that neural networks, particularly if you use redundancy, are able to overcome some of the faults and the radiation that will occur, particularly as we go beyond low Earth orbit. Next slide. There's another way that we can address the radiation effects, and that is to incorporate new devices. These new devices are particularly compatible with neuromorphic computing. One of them is called memristors. That's the second column, and you can look here in the second column that it is pretty much immune to the single event effects. It has very high TID tolerance in the millions of kRads as opposed to that flash memory that I described earlier. And it is going to be ready in conventional fabrication lines either next year or after. Today you can get these memristor arrays that substitute in for the flash memory through special arrangements. And similarly, magnetic STT-RAM, very high tolerance for total ionizing dose, also immune to single event upsets. The way memristors work is you think of it as titanium dioxide, and if you put in a right pulse, it will shift the amount of conductance, and if you do negative right pulse, it will lower the amount of conductance. And there's a hysteresis loop, which is represented here on the bottom right. That means that the read is being done in a very narrow region, and when you do the right pulses, you go out to the edges there. So let's go to the conclusion of this talk. Next slide, please. One more slide, please. Okay, so we seem to have... I seem to be frozen. Okay, well, then I'm going to go ahead and conclude. As we go from the International Space Station to the CubeSats, you're looking at a tenfold reduction in terms of the amount of time it takes to do one of these missions. You're looking at million-fold decrease in the amount of money that it takes, but we do get a huge gap in terms of the amount of power that is available. Through neuromorphic computing, we're able to make up that power gap. We're able to forward base the mission control on board, and with advances in radiation tolerance, we are able to start looking towards exploring the solar system with these low-cost, high-intelligence, sentient small spacecraft. And that concludes my talk.
Thank you very much. Let's go now to our next speaker, and the big question that he's going to answer is the following. Driven by climate change, the severity, frequency, and geographic spread of tropical storms is increasing, and each severe storm can cause billions of dollars of damage. How advanced AI capabilities can assist in emergency response systems and crisis management? Can they assist in prediction of Earth movements? And what about forecasting floodings?
Our next speaker has a long background in geospatial sector. He became managing director of Bloom Aerofilms and VP of operations of the wider Bloom Group. He founded Geospatial Insight in 2012, providing differentiated intelligence products for major clients in the insurance, capital trading, and energy sectors. He is responsible for overall strategy and leading corporate and insurance sector clients relations. Ladies and gentlemen, I have present to you Dave Fox.
Thank you. First of all, apologies, Dave's unable to join today because he's unwell. So my name's Paul Fern, I'm the CTO, and I founded the business with Dave in 2012. So Geospatial Insight is a leading provider of geospatial intelligence services. We use things like satellite imagery, drones, and then we take that data and we apply advanced machine learning and data science to drive analytics from that imagery. So in terms of our markets that we deal with insurance. So we're looking at risk pricing, loss estimation, claims assessment. We look at climate change impacts, and then we do an advisory check on their overall risks. And the area that we're now moving into is green finance. So obviously there's a large amount of changes with the climate at the moment, and a key risk there is the impact on financial assets. So we get involved in monitoring those as well. So in terms of machine learning, in 2016, we developed our first machine learning model. So we picked something that was relatively simple. So we picked cars, which were nicely constrained in car parks. Took about 6 months, big learning curve, but in the end, we ended up with a much more accurate and consistent output than we were getting with human beings. And since then, we've remained at the forefront of machine learning from satellite imagery and aerial imagery. So our latest products, for example, look at detecting buildings and then features associated with buildings, such as solar panels or swimming pools, classifying the different building features into different categories, so the roof type and the roof material. And more recently, we've moved into detecting of methane, which is obviously a very big issue at the moment. We found traditional techniques for detecting methane from satellite imagery didn't work very well, and the machine learning method has been extremely productive. What we did find is with methane is that there's very little training data, so in the tens in terms of kind of the number of plumes that we could get to produce and train a model. So we developed a simulator which created lots of synthetic data, and we had a huge amount of success with that, and we ended up being able to predict plumes to the size of 100 kilograms per hour, which is very, very small methane plumes. And then the next stage in terms of the machine learning that we've been doing is building footprints. So a lot of our products are focused on buildings, and analysis of those buildings and risk associated with those buildings and potential damage and loss to those buildings. So being able to find buildings and then create building footprints is kind of the first stage, really. So this is an area in Africa where we were able to create 500,000 buildings in 15 minutes, which traditionally would have taken a couple of weeks of effort. What we found is that our building footprints are very accurate as well. So ours are on the right, Google's are on the left. This is Kinshasa. And we're producing consistently better output in this area than Google, which is always something nice to kind of benchmark yourself against. Highly adaptable. So a lot of our model was originally trained on Western countries. So the biggest insurance market and the biggest potential insurance loss is the US, and then you've got countries like Japan and Australia, which have very sort of similar building structures to somewhere like Kinshasa. But the model did work very well there, even though it had very limited training data. So that was something we were very pleased with. Now, one of the core areas of our business is cat response. Traditionally, this is all done very manual. We've done 85 different events now, ranging from flood is the predominant one, and windstorm, and then we've also done explosions, wildfires, and earthquakes as well. Now, to be able to do a cat response, what our clients want to know is what's the damage to individual buildings. So the first problem is identifying where these buildings are. So we developed this property view product, and the first stage of that is taking our building footprint classifier and locating and then generating the building footprints. What we then do is we then start to look at the different features of these buildings. So how tall are they, for example, and how many stories there are, what's the roof material, what's the roof type. And from these different values, you can work out what the potential building reconstruction costs would be, and therefore what the risk is for the loss of that building. So this forms kind of the first stage of any analysis we do when it comes to cat response. But what we found, I mean, we've only been going since 2012, but we have seen quite a sea change, certainly in terms of the intensity in which hurricanes pick up. We've had a number of instances where we've been at risk of having to respond to a Cat 5 hurricane hitting the east coast of Florida, where you're looking at millions of buildings being damaged. Now, if we're responding to that manually, it's just not physically possible. So what we wanted to look at was, is there a way that we can use EO and AI to solve that problem and make it much more scalable, much more rapid, and much more cost effective to produce results. So the solution for us has been a combination of high resolution imagery. So this is both satellite imagery and also it's aerial imagery. And what we have is we have a pre-event image. So we know what the area looked like prior to the natural disaster. And then we have a post-event image. And then what we do is we've taken our property view product that generates building footprints, and then we've modified that to be able to provide super quick loss assessment following large windstorm events. So why are we not wanting to do manual damage assessment? So having done this a number of times, it's very time consuming, very expensive. So if you're doing a large hurricane, you might be spending a week with 10 people manually having to assess the damage caused by the buildings. Critically, human beings have all their own little individual quirks and biases. And so the real headache we have is that you get inconsistencies between different people. And so you'll find biases throughout the data set, which can also be a problem, especially for our clients. And ultimately, it's completely unscalable. So if we have a really big event hitting Miami or somewhere like that, then we just wouldn't be in a position to deliver to our clients. So in terms of the automated damage assessment, we've stuck with a FEMA classification, which is no damage, affected, minor, major, and destroyed. So each one of the individual buildings has to kind of sit within each one of these categories. And then combined with the property view product, we can make an assessment of what the likely cost of damage to that property will be. So this is just kind of an illustration of different classes. So no damage, obviously nothing has impacted the property. Affected, what you tend to get is a few missing tiles off the roof, perhaps loss of guttering, things like that. Minor, you're starting to actually lose sections of the roof, but the property is structurally sound. You might be getting a few cracks in the structure, but all very repairable. Major is where you've got one or more components where you've got structural damage. That'd be loss of roof joists. That might be a wall collapsing, for example. And then destroy is when the building's effectively down to the foundations. So what we've had to do is we've annotated 60,000 images, and then we've used that to train a model which is now fully operational. It's very, very quick. So within minutes, we can assess the damage caused to a portfolio of properties and then return that back through to our clients through an API. Accuracy is better than human beings, and critically, no bias, which is really important. So in terms of the models, this is the current model based on ResNet. Takes a before image and an after image, which we call blue sky and grey sky, and then it produces a damage value. So 4, for example, would be a destroyed building. What we're moving now is towards a damage segmentation model. So if we categorize a building as destroyed, it could be that only half the building is destroyed or a quarter of the building is destroyed, which from a client's perspective is very important, because if I'm an insurer and I'm insuring a property that's worth, I don't know, £1 million, and only 10% of it's damaged, then that's completely different to a property that's 90% damaged. So the damage segmentation model basically will tell our end customer that 90% of the building has been damaged at category 4 rather than just saying category 4, which allow them to get much more accurate loss assessment than they do currently. In terms of accuracy, so the confusion matrix here, so considering that these classes are quite arbitrary, so how do you tell the difference between affected and minor when it's just a difference of that one's got a few tiles missing and that one's got a cluster of tiles missing? So it is quite difficult. But we have got a very good confusion matrix. We're very happy with the results, and certainly the clients that we've been delivering this to have been really impressed with the output that we've been achieving. We do other perils as well, and we're expanding the capability to do that. Flood's quite tricky because usually with flood, the floods, when we capture the floods, usually the floods have started to recede. So there's lots of kind of manual interpretation, and that is quite difficult for a machine to do. So you're kind of looking for dirt, you're looking for sort of tide lines at buildings, you're looking for piles of rubbish outside buildings where they've removed the interior carpeting and things like that. But wildfires have a similar sort of pattern, slightly different to windstorm, but we can adapt our model to work with those. And then more recently, we did a test in the Ukraine as well, just looking at shell and bomb damage to see how well the model carried over for that. And in this particular case, yeah, it did classify it well and showed a pretty devastating picture of what was going on in this region. So in terms of conclusion, what we found is that the combination of access to imagery and then combining it with AI has a potential to radically change the insurance sector following major weather events. So it's going to allow our customers to resolve claims much quicker, which is a considerable amount of the cost that they incur following these events. And we already have contracts with a number of major insurers and reinsurers to provide this service. And this system's now live, ready for the 2022 hurricane season. So thank you.
Thank you, Paul. That was a very interesting presentation. Now we're going to, as we're marching down the paths of Silicon Valley, as we said at the beginning, we looked at the perspectives from the governmental point of view of the applications of artificial intelligence, from the industry. We had the Intel expert here talk about neuromorphic technologies. And now I want to bring on the table here Woody Gibson to discuss the entrepreneurship, commercial space in Silicon Valley. So Woody Gibson is a Sander Black of Silicon Valley. He's the person that coined the term clean technologies, clean tech. That's Woody Gibson. He's a serial entrepreneur. He founded over 14 technology startups in the energy and environmental sectors. He recently founded and serves as the Chief Executive Officer of Spacecom Global Incorporation, focused in space communications and the use of artificial intelligence and for its data analytics. As I said, he's a serial entrepreneur and he founded multiple companies and took them public. For instance, I'll give you a few examples. He founded Smart Wires, that is listed in the Swedish OTC exchange. Zenergy Power, having listed in the London exchange. He was the founder and SVP of business development for Thorn Environmental, a US remediation firm, where he was responsible for identifying and incorporating new technologies. Woody also served as a general manager, special projects planner for International Technologies Corporation, ITX, listed in the New York Stock Exchange. And he played a major role in helping grow revenues from 2 million to 1 billion in 5 years through acquisitions of new companies. Currently, Woody is a senior partner to Jane Capital in San Francisco and also Green Solutions. Please join me in welcoming Woody Gibson in this panel discussion. I will also invite Marcus Murbach and Zam Mouillard and Garrick as well to be part of this panel. And the intent here is to spark a dialogue with Woody and give us his perspective in terms of commercial space, space financing, and so on and so forth. Here's a minute to set up the panel here. Can you hear us? Okay, so, and I think we have remotely Garrick as well. He's part of the panel discussion here. So I would decide to make this a little fun. And we're a little bit conspiring with Marcus here and Zan to tag up on Woody here, since we got the unique opportunity to corner him. And the kind of question, we're gonna circle and create a dialogue, very open-ended. We try not to box any discussion here. The questions will be very general, so allow Woody to expand on his thoughts and perspectives. And I will kick this off. Every system, space system architecture, we said requires system integrations and multidisciplinary discipline integration of multiple different subsystems. It requires systems thinking. And the process goes, we have the known knowns, we have the known unknowns, and then we go into the unknown unknowns that we have to make sure we address for every system architecture. So the first question to Woody, and I'll keep it very simple, is so what? Every step of the way going down the system integration, we come up with these what if scenarios to address the known unknowns and the unknown unknowns. And then, so what? We did all these beautiful presentations from our community and all these perspectives. Is that important? What are your perspectives, Woody? What are your thoughts?
Well, it's been an honor to be here. And when I'm not here, I'm watching this on video of all the presentations. And my whole idea of being successful in this field is to build a platform and add technologies and people, resources to it. Sometime, as I said the other day, I feel like a kid in a candy store. There's developments going on super fast now. And so you have to, if you're going to build a space platform, and I look at this, of all the platforms I've been involved in building, of picking the right people and the right technologies for the right application. And I had my first taste of space back in the Gemini series and recovery. And I got the space bug then, but I couldn't figure out how to get involved in it. NASA pretty well had that under control. But I followed it intensely, and I ventured off in the climate sense and environmental, clean tech areas, clean energy, power delivery, and so on and so forth. But everything pointed to satellites and what you could do with satellites, and making satellites smart, very smart. And this whole conference has been very interesting to me, and I'm sure many other people, because it's pointing out what technologies are available now and what's going to be available. And it's very encouraging for myself and our platform, Spacecom Global, because we intend to blanket our whole system with AI. We've seen some remarkable neural networks, smart agents, and how that interfaces AI, the software, hardware, and better just today is the low voltage requirements. So everything gets smaller and smaller, launching satellites and rockets. The smaller you can make it, the better price you get into space, the more small satellites can go up. In years, it cost $1 billion. Now you're down to $1 million to launch a satellite, as low as and possibly even lower. So if you get into the shoebox size, but we're very excited about it, and I think we're going to help be a change agent. And what you can do with satellites is almost endless. And I point back to artificial intelligence. You have seen, if you're watching this conference, or go back and review it again, marvelous changes in AI, and how there was one presentation today of Thought AI that emulates bees in the biological world, and the neural networks that say Intel is making, and innovation. These are unbelievable, and it's going to help us tremendously. That means you can hit the running, projections of getting a satellite is up to 2 years. Now you probably could get a satellite up starting next year in 6 months, if you can get a ride. And there's plenty of rides going to be available in Europe, and we're looking forward to being more Eurocentric for a lot of reasons. And even though we're a U.S. company, we're going to integrate ourselves more into Europe, and Luxembourg, for instance, is supporting that sort of thing. So I don't know. This is my philosophy and how I'm looking at it. Thanks for the question.
Want me to answer that particular question?
No question. You can answer.
Or Jean? Okay. Well, okay. So let's try this one. So this year, until the debacle of February, the world economy was going to touch 100 trillion for the first time. So rather remarkable. We saw in one of the earlier presentations that we're now in the hundreds of billions of dollars in terms of the space economy, and it's going to grow perhaps up close to $1 trillion in the next 10 years. So could you elucidate some of the, where we're going to be in 5 or 10 years? What are the technologies or the disruptive technologies you think that are going to greatly help commerce and perhaps humankind as well?
Well, launching with clean technology is on the horizon for us.
Okay.
And launching, moving the payloads into space is the curve is going down drastically, thanks to Mr. Musk and SpaceX, and ride sharing available. In Europe, there's several ride shares that are available, and more come in the UK. So that just drives the price down. And getting into space is going to be a lot easier, a lot more clean to the environment, so to say. And we're very jazzed about the philosophy of clean or climate sense, sorry. And we just see that with the satellites and what we can compact into one satellite, geosensing, hypersensitive sensing, and the computer sensing. I've just noticed that there's solar flares going on very intense. Usually it's a 10-year cycle. We're having more now. It's going to affect the climate change, but it's also going to affect satellites. They're going to be dropping down meters per day. And so it just takes fuel to re-up them. I'm encouraged with the ion drive motors without using chemicals that's going to run out. If you have to do a lot of maneuvering, stay ahead of solar flares and so on and so forth. And the protection that NASA Ames, the question here is doing is very important to us. Miniaturizing, using less power. That means that we can get up more satellites and create your own environment. And this will be, for the deep space benefit too. A lot of people going to the deep space. These inventions or technologies for miniaturization, low power processors that can process with agents and also artificial intelligence to make satellites more autonomous. Recovery, they can fix themselves, so to say, reboot themselves. And but I think we're on the edge of a total new revolution, and keeping our eyes on our. I look at the Earth as a spaceship, and we got to take care of our spaceship, and we need to keep an eye on it. And the best space is up about 500 kilometers, 1,000 kilometers, but then there's the big boys that are about there in the geo, 25,000 miles or so, that have their purpose too, to cover more areas for climate. It came to my attention about this year is that we have a lot of gaps, Indian Ocean, Southeast Asia, that we're not able to see what's going on. And climate is changing. The country of India is evolving. They're putting up rockets, but people need to look in their own backyard. Africa has been neglected a long time. So we need to know what's going on in the Indian Ocean. They just have, with climate change, one storm after another is coming. And it's happening so fast that remember what we said here today is it will be faster and faster in climate change, and it'll hit you so fast and so hard. And so that's why I'm in it. A couple of years ago, I decided that I've kind of accomplished the thing I wanted to do in environmental and clean tech. And I got the space bug. And it's like drinking from a fire hose, the knowledge. It's so much to learn, and never stop.
Perfect, Woody. Let's challenge Mark now, and then we'll go to Zhang.
Okay.
Woody, why don't you challenge Mark a little bit?
Okay.
In terms of so what, Mark?
Well, Mark, when is your technology going to be available? I'm the buyer.
Well, we're ostensibly the government. What we're doing is we're making all the forward mistakes and advances so that people like you and in private industry and academia can take advantage of it. So we're the government. We're supposed to be on your side. So it's certainly available. I don't know if you were here early enough, but we brought some of the pieces of hardware that we've made available showing how all these things work. But the whole idea is, for example, if we happen to be the first to fly For example, the Intel neuromorphic chipsets that are rapidly evolving, as you saw today, then you or commercial entities or academia will learn how to do these and benefit by the mistakes and the evolutions that we've done. So we have part of our team in the audience. Do you all agree with that, or would you like to embellish? Okay, I got a couple of thumbs up, 3 thumbs up, 4 thumbs up. Okay.
Okay, Mark, propagate the dialogue here. Maybe you can ask Jean your question and
All right.
provoke him.
Sounds good. Okay. So my dear friend Jean Moulard, Dr. Moulard. So we human beings are incredibly inept at predicting the future. We see the shells of companies all over Silicon Valley. One of my favorite happens to be a once great was a workstation company that was essentially at its height, right outside of NASA Ames. Their inability to predict the future resulted in the fact that their main office building is now the museum, the computer history museum of Silicon Valley. That's amazing to me. It's a great, perhaps unfortunate example. So Jean, where are we going to be in 10, 15 years? What do you see other disruptive technologies? Because we've talked about a whole bunch of them. My presentation earlier showing that the CubeSat was essentially a pyramid of many disruptive technologies. What do you see?
Thank you, Mark, for this intriguing question. Before I answer specifically where would we be in 10 to 15 years from now, let me just address some needs to be able to achieve in 10 years, something good that is for mankind, interesting and needed. The first issues I see is, in addition to the big digitalization of the world and the globalization of the world, and that's where Woody came in with the Spacecom global vision, is due to the digitalization of the world, the need of collaboration with industry, military, and public entities, and advancing the transition from data to information using AI algorithms and so on. But due to the digitalization of the world, I see also an enemy arising, and that is the resilience against cyber attacks. Because the globalization asks for collaboration of different groups of people. It asks for supply chain rules, which is off the shelf, versus if you look into the military grading and authentication of up to the microchip level, this will be a changer in the future. And so my concern is between now and 10 years from now is how could we assure a more safer world where we are convinced that collaboration between the nations and the people and the different groups is a need, but how could we assure at the same time that we are having no fake data? The word was used many times these last 3 days, but also that we have assured, authenticated data on which decisions will be taken. Just a minute ago, these very nice presentations on space for crisis management, man-made or industry pollution-driven issues. You can imagine that if you see all these wonderful data but what about hacking and spoofing and jamming and so? And it's a tremendously increase in the world on that issue. So my concern is also, shall we be able to cope with these enemy issues? And of course, then thinking ahead in 10 years, your basic question, of course, I hope that we will be able for our children to have a world where communication is safe and fast and cheap. But we better work together today in those items where, first of all, collaboration is absolutely needed between Europe, US, and the friendly nations, so to speak. Look at what's happening in Ukraine. I'm dead scared about what is the outcome of that. But at the same time, being realistic and do the developments today that, we realize that the quality of a pixel, the information, the authentication of it is very important. And it's going to be like, I don't know, like an overhead, 10, 15, 20% overhead that we need to accept this. If you want to have good data, it's going to be more expensive. And at the same time, so this is a little bit my concerns. I don't want to terminate pessimistically, but I'm sure the technologies today, what we see, will certainly allow us to cope with those things. And what I've very much liked is that we see a much stronger collaboration between science, the lower TRL developments, and the applications through these kind of workshops. So we should have more of these to accelerate, the TRL up to 9, up to the real applications. So I think it's going to be very fascinating in 10 years to see a quite different world. And it's very good for the universities, the students, for the developments through international collaboration. But with my concern is the resilience against attacks, the robustness of it. And so this is why I'm very keen on listening to Woody as well about his vision of space come global, the need to work together, the important role of AI, and how can we follow that path in addition to making sure that we have a more secure world.
A more secure world, I think that's very much on our minds right now. So that's important. Do we have any of our guest speakers that are still on? Perhaps Dr. Orchard is not, but we were going to ask him, what does the Loihi number 3 look like? We talked about the Loihi 2. So we'll save that for another session in the future. So we've seen some super rapid advancements of the hardware and the comm. As we increase the bandwidth of the comm, that's going to the encryption will perhaps be less of a burden, I think is the idea. So as we can expand that, that'll be important. But on the other hand, if we're taking a lot of environmental data that we do we need to encrypt that, or is so somebody's got to for the launch vehicles and the satellites, et cetera. But Planet Labs has been able to have a pretty good business model by just having their fleets of, I think they're called doves, essentially 3U satellites at first, and they're able to actually have a resilient business with that, basically just selling images. They're not quite spy satellite quality, but they're quite sufficient. So. Do you see the necessity, pardon me, to encrypt environmental data that we could all use and all be careful with, so that we can actually be careful about the climate changes?
I think everybody should realize a satellite can collect all data and images in the world. Some people are very sensitive about that data that's collected. And so you don't want to get in trouble with certain countries and war zones and so on and so forth. But, we collect 100%, imaging and so on and so forth, high definition imaging. That's why you need AI to sort it out. You may probably only need 2%. Or we go to customers and we say, what do you need? Or we tell them what our capabilities are, or we can develop the capability. But it's important to from a commercial standpoint, that you give the customer what he wants. And every customer, like a television station, weather reports, NOAA doesn't necessarily give you all the data you need. Their satellites are antiquated. There are going to be better satellites up there, but when you get into lower altitude satellites, in the LEO range, say 500 kilometers, 1,000 kilometers, one satellite doesn't cover enough area. So the big boys in the sky, the giant machines up there to 25,000 miles, they can do the work of 1,500 small satellites in certain services. But, they can cost up to $1 billion a piece, and they'll last 15, 20 years. So I think what the bigger play is figure out what kind of fleet you need. I'd like to see us get 4 to 10 satellites up next year, and see. We know that we know what some customers need, but I think from a commercial standpoint, it'll be more of a competitive world for it. But if we put the proper security in the system, we give the customer what he wants, and we're constantly trying to have that dialogue with banks and insurance companies, Swiss Re, the reinsurance market. They have different reasons for lending to people, checking their risk factor, the insurance company underwriting with all these storms and the climate changes. It's become a risk adverse of monetary situation, very dangerous for commerce, and even methane. It's been released from chemical plants, the danger of plants blowing up in population areas, being able to keep an eye on these things, land subsidence, temperatures, icing of clouds. It just goes on and on and on and on. The commercial applications and opportunity is probably the best industry I've ever seen. Much better than the environmental industry and so on and so forth. So I feel there's no doubt we'll be successful in what we're doing.
Great, Woody. Thanks for those comments. I'm going to kick another second round of dialogue here. Okay. Again, this is open-ended. I'm going to start by asking Woody again. He was the founder of CleanTech. He essentially created a movement around clean technologies here in Silicon Valley, and also created the financial instruments to fund all those startups. Now, from this knowledge from CleanTech, now you pivot into space tech, let's say. And as you say, this is a candy store. How do you see the implementation of these financial instruments that you used in CleanTech being transported and used in the space industry? What are your thoughts?
Well, what we see is we spend a lot of time educating our investors, potential investors, and sometimes it gets a little frustrating. And it used to be a lot easier with the environment, but I think people are becoming more aware. The investors, the VCs, the banks, and also family offices, impact investors. It's just a matter of getting the message out there and convincing them that, yeah, we're worthy of their investment. We're going to be good stewards of their investment. We're going to treat their money like we're spending our own money, and be responsible and return. Everyone wants to return on their investment. So, but we have to make it commercial viable. I'm encouraged. It's been a long path the last couple of years to finally get to where we are now. I feel very comfortable that in the next few months that we'll be able to close a lot of our platform. When I say building a platform, we're kind of agnostic of technology. If we need it, we work it. We try to build these relationships with companies that want to be a part of what we're doing. I always saw that a lot of good companies out there have one or two little technologies or patents or something like that. By themselves, they're not that commercial. But together, if they team up or they join a platform that eventually could go public or something like that, it's, in other words, you're baking a pie. You start out with a little pie and you end up with a big pie, and everybody gets a nice share of it. So hopefully this conference will bring a lot of investors to the table. Hopefully a lot of them watched this conference and saw what was possible and who has what and who to go to. And space is open for business.
Thank you. Thank you for this great question, Perry. And the answer of Woody is very much appreciated. As I have been all my life in the development world, you know, from the universities to the space agencies, where the job of the NASA and AIIA, by the way, is to establish an industrial infrastructure to make the space missions a reality. And my concern is now for the future, as we are talking about finances, is that when you only look into a return on investment, which is of course a short-term vision, that it may unbalance the scientific developments, the university developments, the research establishments. So how could we, for the longer term future, make sure that this balance between short-term industry-driven investments for return, so economically seen, how could we also at the same time assure a longer-term, more scientific developments? Those in many years from now will be used, because in times of crisis, as we have seen this in Europe, we have seen this everywhere, that when the economy goes, or when inflation is high, or when the economy goes bad, you know, it's all return on investments. There's no money anymore for universities, for like music. You know, you can do research, maybe not really exactly know what it will be used for. And yet today we've seen these morphological technologies, this the tremendously advances of AI, which thanks to some past investment in this domain, now we can take profit from. So I'm always concerned about the balance between short-term businesses, return on investment, and allowing another community in this world to do science and technology and research for the longer term. So we need an institution, or we need somebody who watch this carefully from the top, I think.
Well, if I can add on that, actually, part of it is that we have a space industrial policy. So, you know, the governments of the West in particular, Japan, et cetera, we are investing tens of billions of dollars each year in a kind of a base infrastructure, of which I and you, Jean, represent. So there is that. And then, as we mentioned previously, part of that is to keep on asking questions, essentially taking looking hopefully at the higher risk elements, so such that we can advance science and technology, and then that's harvested then by the private industry that can actually go in a particular direction. So, this is harvestable. Let's do this. We can turn this into a multi-billion-dollar industry. And so we're seeing that. So there is a balance. Whether it's the right balance at the moment, you know, this is a question, but it's there. But that was the intention, was to make it harvestable. And I think we're doing a reasonable job, I believe.
So Mark, maybe I can put you a little bit on the spot on this comment. I'll let Woody after that comment. You know. NASA for many years had this, if you can imagine, two S-curves that cross each other. One is the funding from the government, the other one is the funding from the private industry. So it starts with big flag missions, primarily funded by government, very expensive missions for interplanetary explorations, and very small contribution from the private industry. And these two curves that converge, and then there's a pivot point, and then there's switch over, where on the other side, where the industry is leading the way, and the government is supporting that lead. So anything LEO all the way to moon exploration, it's on the commercial space. And I think Kelly Candice did a pretty good job from the Space Foundation kind of laying that out, you know. But we have the tendency, and there are two keywords in the space industry that we name two probes on Mars, curiosity, and perseverance. So I want you to use those two words. And the other thing we say as space engineers, that space is the lower limit. Sometimes we say sky is the limit. We say sky is the lower limit for us, okay? So I want you to build your arguments looking forward, like you asked Zan, what do you see 10 years from now in space exploration, commercial space? Is SpaceX, Elon Musk will be the first to colonize Mars? I mean, what are your general thoughts in this direction? And then I'll let Woody take the lead after that. So why don't you start, Mark, and then Zan can continue.
Very good. Those are, let me parse the questions a little bit. For one is that humans on Mars has been a goal for many decades. Actually, what this other presentation I like to make once in a while show how we could have been, humans could have been on Mars in 1982 if we'd considered to continue the Apollo program. And so that's a really fun thing to take a look at. All the infrastructure investment was there to do that, which is surprising. Why we didn't is also surprising. But here it is, decades later. We're on perhaps the verge of that. I'm agnostic. Whether it's private industry using a lot of NASA techniques or technologies or ESA's technologies to advance, I think that's just fine. If it's a company like SpaceX, this is Mark Murbach speaking, not NASA, of course. But I think most of my colleagues would be very happy to see that, because that's going to be another tremendous step for mankind, if I could. But again, it would be on the pyramid of a lot of technologies that would have been harvested. So, but he does point the way in some senses. The fact that we've now seen recoverable, reusable stages. We've seen the papers on that for many decades, but it took some grit in order to bring that about, because it would have been difficult for a government entity to directly take the risk and basically have a lot of mishaps on these barges as you try to essentially master the technique of recovering those boosters. Once it happened, then we see a tremendous decrease in the cost per kilogram to low Earth orbit, and that's enabling, as Woody's pointed out. So we see a lot of that. I think we want to go to Mars. I think that's going to be more governmental. But what happens with that, and the analog is with the Apollo program. One of the biggest benefits of the Apollo program was actually in the case of the United States, it showed the highest number of PhDs in the technology fields, because it was so inspiring. And so a lot of my colleagues in the audience over here certainly are in aerospace and those disciplines because of the interest, the curiosity of doing that. So to me, the Apollo program, that was one of his biggest beneficiaries. In that particular case, the journey was almost more important than the destination. Okay, and I think it'll continue to be the case as we look at Mars. We'll have to master some other technologies, or not. We could have done it the way that von Braun and NASA were proposing to do that for a 1982 landing. We could have done that. Guess what? Without AI and machine learning, it would have been something a little bit different, a little bit more gritty. It could have happened. Now we can harness a lot of these advanced technologies to hopefully bring the cost down, which is one of the primary reasons why we didn't pursue that.
One of the successes I've had in the past is mining universities and national labs. And I give an example, SmartWires company that started, I spotted a PhD student at Georgia Tech working on something at the bench, just going through the lab. And I said, well, that looks interesting. What do you do? And they said, well, that controls power flow on the grid. And I said, oh, really? That's pretty ambitious. So I went to his department head, and I said, how much it cost me to sponsor this guy for another year to work on what he's doing, to develop his patents? He said, well, about $60,000. Well, today that 60,000, 2 patents is almost 1,000 patents, and it's over $1 billion company just from that one PhD student. And then when I did superconductor business in National Lab in Sandia and Los Alamos, it's amazing what they have on the shelf that they were allowed to invent and stuff like that. People need to shop NASA and the national labs. Look at all the benefits that come out of the Apollo program of inventions that people use every day. They don't realize that was paid for by the government and inventions and things like that. So I kind of feel like I'm a shopper. You know, and I keep saying the kid in the candy store, but there's a lot of good technology. We're integrators. We're not going to be doing R&D. We're going to buy R&D that somebody's looking for a buyer or investor to bring it out of the labs to put it into space and so on and so forth. And I think that's where our great success will be, and that will help the small guys. And you know, there's a lot of great young inventors out there working on some really cool stuff. And
some are out there.
Yeah. And so we're the people who want to integrate that, want to buy it, and we have some very smart people that know what we need to fill gaps. And we're going to keep our eyes on a daily basis. So I think that's going to be our key to our success.
Thanks, Woody. That's very well said. Let's go through a final set of comments, thoughts, remarks, very open-ended. Let's start with Zan.
Okay.
And then...
just a final remark on my side, Perry, what you were saying, and Woody, is that I see space really, we are in fact at the beginning of a new era for the future, which will be different in the sense that it's going to be a hybrid, really a hybrid space business and communication. Think about the future of quantum key distributions, quantum computers, laser communications, and as I mentioned, and we mentioned all together a few times, this globalization of space. And the effort in the next 10 years will be using space for our Earth with new advances, new technologies, new Earth observations, but at the same time, new space laws, new governance, because we talk easily about combination of LEO, MEO, and GEO, private constellations, you know, from Bezos and Elon Musk, and then the institutional missions and constellations. And so it's going to be a mix of all that. But we also need to be prepared and develop faster the governance of it, the law, the rules, the frequency allocations, because all this is in the process of being used. So space will be, well, I don't like the word commercialized, but it's going to be inevitably that it will be the case, but but also using good laws and good governments, and taking into account also the things like we saw today, debris mitigation, but also meteorite impact, in addition to the deep space missions, as you were saying, Perry. So I think we will still be watching and taking care of our Earth with more hybrid tools. Thanks to the AI, thanks to the power computers, thanks to the algorithms. And so this complexity should be balanced with an enhanced security. I cannot stress it enough. So I'm very optimistic that these generations will apply their know-how in a more safer, regulated, secure world. Not only this world, but also beyond. Because of course, we're talking about the moon and Mars and beyond. This will never stop, and we have to do this. But the priority in the next 10 years will certainly be watching back our nice Earth from space and use all the benefits from space to do a better job on Earth, including energy. You know, the solar, and we've seen all the developments of laser communication transponding solar to the Earth. So I think I'm quite inspired by what I hear about AI. We are approaching this need of more governments from space using space for Earth.
I think that's a great comment. I think where I'd like to start is for where we're going to be in 10 years. So I regularly tease my my younger and brilliant colleagues, there some of which are in the audience. I tell them, God, it's everything that we're doing, everything we're seeing is so exciting. I wish I was 40 years old again. And they roll their eyes because, of course, to my colleagues, 40 years old is an ancient man. Well, I'm a bit beyond that, but that's the point. I think it's extremely exciting what we're doing. We're in the middle of the new launch vehicles. We're doing very interesting things, and that funny little containerized cargo that we showed earlier. So that's very wonderful. At the same time, the technology is a double-edged sword. As we've talked about a bit during these 3 days, technology gets ahead of governance. It always has. It always will. And so we have to also educate ourselves and be wary, because we can lose this privilege that we have here in the 21st century of the standard of livings that we've worked very hard over many generations and centuries in order to achieve. We don't want to erode this, so we need to preserve that. We need to preserve be good stewards of the earth and use these techniques, these technology, the AI in an intelligent manner, because again, it can be used for ill will as well, to really promote, a better standard of living throughout the world, so that all countries have a higher Gini coefficient as a figure of merit I like to use. So one can be optimistic. Let's not screw it up. Let's be educated about it, mindful of it, mindful of our privilege.
Well, I think one of the big things that's coming to us now is impact investing in country development to help, say, Africa. The European Union is willing to pay for surveying Africa, for instance, several countries, and drought, illegal mining, water pollution, storm damage, et cetera, et cetera. They're willing to give that information to the people of Africa and pay us to provide that information. We have to, return on our investment, so to say. But in commodity trading, there's just so many things that are going to benefit Earth. Keep an eye on coffee plantations, cocoa beans, bananas. Things happen to those, and you're buying them, and you've got to supply your supermarkets, and that was an eye opener that bananas is a big business. And it's a big business for us potentially to keep an eye on what countries growing the bananas, and if it's a drought, if it's an insect situation, or some kind of pollution or revolution problem, especially cocoa beans and areas of coffee. And if you keep, those are businesses that they want information on. And so we're in the business of creating information intel, and that's going to help mankind, agriculture. I think John had told me a story about someone he helped with the EU that's making satellites in Belgium now and sensors. A couple of young guys, and now they're a big successful business very rapidly. And Dr. P, he had some students that created Planet Lab.
Well, Mark is responsible partly.
Yeah,
for the
Marcus too. So you can see the help that people give that are in responsible position, and young smart people. They're our next generation. They go out and create a company literally overnight, and so we're looking for that sort of thing, and to help entrepreneurials and help along with their technology, and sometimes you can't make it by yourself. You need some help. Yeah. So
thanks, Woody. I think I would like to first acknowledge the agency, because I must say early on NASA recognized the power of mentorship and teaming together the young graduates through internship programs and the professionals, and this way generating and filling the gaps in terms of expertise in very specialized and difficult topics areas. for exploration. A mutual friend of ours, Mark, Tony Strava, one day he calls me and he says, can you make an announcement in class? And I'll give you a link to a website. NASA Commercialization Office, and Tony was the head of Code V at NASA Ames. Any patent, any research, that patent that gets created from NASA, it's available to any student, any group of students to spin off a company. That was an announcement I made in the classroom, and several students actually took on the task, to actually investigate that. I think that's very telling in terms of inspiring the new generation, be behind them, supercharge the system, and space requires systems thinking. And I think that's the collective dialogue here reflects that. It's systems engineering, getting more intelligent about things. We're in the era of exponential growth in space. And I think space is really the ultimate frontier. And it's for people like us, explorers, entrepreneurs that look into the future. And in my mind, a lot of our careers has been around space, and we will be still children, Mark, regardless of the age, And I can see that between us all, I think that's my final remark, and I truly want to thank the panelists, Woody most of all, for representing Silicon Valley at its best, Mark representing the government, NASA, and with all the innovations, Zan representing so many things in Europe, Von Karman Institute, Director, European Space Agency, NATO, European Union, the list goes on. But thanks to all of you for a great dialogue and discussion, and looking forward to continue our discussions further.
Thank you. Thank you.
Thank you.
It is evening now in Athens, and let's now move into decentralized finance action as it relates to artificial intelligence. Finance is something that's very close at heart for me, being involved in banking and finance in general, and having experienced centralized banking for over 2 decades now. Very refreshing to move into decentralized parameters, which can make things more conducive to competition, sound investment, bringing funding in. And so this is why I think this next discussion, these 2 next speakers we will have, will bring some great insights into this whole debate. Allow me to first introduce Mr. Mru Patel, CEO and founder, My Tokenized Capital, and eWealth Tech. Mr. Patel is a business visionary, disruptor, fearless serial entrepreneur, best-selling author, and award-winning public speaker with skills and experience across various markets. He is a graduate in computer studies and has over 35 years of experience in technology, property, investments, and development. plus over 20 years of experience with blue chip organizations like IBM, Sun Microsystems, and Siemens. He left the corporate world to set up his own property investment fund in Eastern Europe in 2004 as the first major independent fund in Romania. Mrupatel's professional journey continued in the revolutionary blockchain field post the property and financial crisis of 2008. The journey to his vision of be your own bank and wealth manager started as a proud leader and visionary for open source movement with Sun Microsystems in the 90s. He has been involved in several startups at board and advisory levels in technology companies starting in the late 90s and continuing with digital banking, decentralized finance, crypto exchanges, etc. Please allow me to welcome Mr. Mrupatel so that we hear his insights on the subject. Mr. Patel.
Hello, can you guys hear me? Great. Can you see the slides? Can we see this? You can see the slide as well, right? Great. So, Angelos, thank you very much for a very long introduction. So thank you. Just to summarize all that, over the last 3.5 decades, I'm probably blessed, I guess, for want of better words, where I've been right at the heart of vision from some of the biggest disruptive things that have been happening in our time, specifically the whole start of decentralization, specifically internet and .com, where I was at Sun as a visionary and a business leader during that early .com days. This is well before Google, eBay, Amazon, all the usual households even existed. So we're right there at the early days. And from there on, it was my passion how to touch more than 1 billion people's lives and more importantly, how to impact them. So in that journey, having finished my cooperation, for one of better words, in the corporate world, I said, look, this is bigger than being in one single corporate. I want to do this via an investment fund, and I want to touch as many people to make the world financially inclusive. A little bit about my background, why it's a passion for me. I was born and raised in Kenya. My father was born in that part of the world in East Africa, and my grandfather went there in the 1890s. So I would say I'm more African with an Indian heart and soul, right? So obviously Indian origin. So those two big subcontinents, are the places I want to touch, and that's over 2.5 billion people. I think I can touch, and where I want to take this now is into a totally disruptive, financial inclusive manner with a huge social impact. And the cliche that everyone talks about is the good old ESG compliance and certification. So what we are building just now, using all sorts of technologies and partners, especially AI and ML, because I started that, for those of you who remember Yak and Lisp in the 80s, I have been involved in that and moved on and following all the way up to what we're currently using is Python and all the rest of it. So what I am doing in that mission is to make sure that where people like, and sorry to say it, I used to be in the Valley as well, my previous friends, I would call it, who are now in the Google, Facebooks of the world, and Oracle, obviously, as well, where Sun Microsystem now sits. I want to totally disrupt that whole business model. What do I mean by that? So where the product, okay, now imagine this in a poorer country, we the product doing like, comment, share on all sorts of things from YouTube, Facebook, TikToks, what have you. We don't get any money from it. We see the ads, we see all that. So the big tech are making all that money. set of leaders, as well as the next leading technologies in the vision that I have. Okay, so even in the ESG space, one of our partners, Save Planet Earth, we're doing everything from waste to compost, biogas, all the usual solar, wind, and hydro-based energy. We're also doing lots of recycling projects, and then on the planting side, we've got God knows how many million. At last count, it was a couple of million trees, and it's going to grow exponentially now. And converting those into carbon credits, but more importantly, some of the new technologies using AI and robotics and even drone technology, where we, for example, boil seeds up with some compost and some coal, where we can just drop them using drones to replant very fast. Okay, and then the AI technology will calculate and learn the growth, the conditions. IoT technology is also used there, where how much sunshine, water, nutrients, blah blah is taken, and the growth of that tree plus the other subterranean things that we grow on that same terrain. So it's reused for other things like fruit trees underneath, and even low growth things like lettuces and things like that. Okay, and the IoT device with the AI technologies as well will give us all the measurements and data points for us to improve it constantly based on various factors, not only from the nutritional factor, but the whole supply chain of if it's a fruit or a veg we're growing, all the way through to the wood and the quality of the wood that comes out of it after 10 years or so. Okay, but then how the carbon works, we are taking it to another level where the carbon credits from that we are converting into NFTs and tokens, where now people can create wealth by owning just a piece of it. So it's not for the super rich always. We want to make it more inclusive through our ecosystem. Just a small example there. For the subject matter over here on the banking and wealth creation, and the impact where I see is, if you look at most banks, and I've done banking solutions, including CRM and AI in the 80s, with open banking when I was at Siemens Nixdorf, for that matter, in the 80s, where we developed some CRM tools in those days with Crystal, if I remember right, how to engage better with your clients. Just now, loyalty for banks is just one click away, in my view. People have lost loyalty because, my view, banks have no clue on how to engage properly with the data they have with their clients. So there is very little value add to their clients and very little engagement with their clients, apart from doing the odd online banking, statements, and that's about it. If you're a high net worth, they will say, I'll give you a customer relationship manager who wants nothing to do is sell their products, be it loans, wealth creation, which is often a single digit percentage, or something else. But product focus, what I call this is the products, go and sell it, rather than innovative ways. What we are developing is we have a neobank. It's the second one I'm doing, integrated to an exchange which will have digital assets as well as fiat traditional assets, including tokenization of mines, and it could be anything from gold or oil. And then my vision for that is how everyone can be their own bank and wealth manager, and everyone has a value. So my mantra there is everyone can be the coin now. Okay, so what I mean by that is everyone has a value, and I call that how to bring my real world assets and real world universe into the metaverse. That's what we are developing next, using all the different tech that is out there, and AI happens to be at the heart of this. So I'll give you a quick example. What we're developing there is in the touch points. Take me, for example. I love music, I love movies, I love X, Y, and Z, restaurants, watches, blah, blah. Okay. I collect lots of autographs, signed memorabilia, things like that. There are so many people in Africa, India specifically, who have so much talent and skill, but they follow these big celeb levels. Anyone can make Ronaldo and Messi even more popular, and these guys get nothing for it. Only those guys get the money, and the tech providers, the YouTubes, Googles, Facebooks make even more money based on ads placement. We are doing a total disruptive platform. Two of them are already finished, including the sharing of the ads revenue to the community and including the share of all that content that is absolutely key, where even if someone does a small video clip or a dance routine or a piece of art or music or whatever it is has a value, and then create their communities, and we call that entering their own bubble and their community and developing that next level AI, ML based, market sensitivity based, your own real universe based of social media to disrupt not only the social media and the metaverse, but to bring it real rather than just digital. I am not a very big fan of all these NFTs, even though we have an NFT platform. I'm not a big fan of just a pure digital NFT. I'm a fan of real world NFTs, which has value that you can do something with it, include earn revenue whilst it's sitting there in your collection. So that's where we're going with the real world. And then if you think about what's happening in the future, we take all that big data we have, because what most banks don't know and can't do, purely because in my view it's internal politics, saving people's seats, pensions, and what have you, and that whole cartel that goes around it, which will be disrupted because they don't want to lose control. You have to phone someone, send an email to get some information. Ours is a total open, transparent, decentralized way with proper regulations, with proper GDPRs, through consent. People will be able to earn and make banking free, or rather, I say, we pay you to bank with us, because you should now own your data. Your data is worth more than what the banks give you credit for or what the social media give you credit for. All right. So that's where we are disrupting using these sorts of technologies. So for instance, if I was a bank or a social media, I have a digital footprint, I have a digital walk, as we call it. And in that digital footprint and walk, we know that this person likes to travel, he likes to buy watches, he goes on holidays, he likes to eat in restaurants. Or if you're from a different part of the world, they know this person goes to school here, he likes to follow Ronaldo, or he likes to study about physics and chemistry and all that. And then you know that they spend X amount in a local corner shop, or Y amount in the local club, or they go to a movie. So you know that spend, and you know their ambitions, you know their vision, you know what kind of things they search. Yes, it's policing, but it's through consent. If someone wants to earn money and doesn't mind sharing that, but they have that data without giving people's credentials out, the market stats and analysis for collecting that and sharing it at the market level with the consent under all the usual GDPR, etc. rules, they can earn money based on targeted ad placements and geotag based ad placements, or following for doing upsell, cross sell if you're a bank, and things along these lines. So that's the fintech kind of space. Now, the same thing we are doing in all of those sectors that we are investing in. I'll give you a health tech example. There's telehealth, telemedicine. But imagine if we owned our data. So I have XYZ conditions. I take ABC pills, and this is my health condition. This is my age. This is my statistics on my everything to do with MRIs, scans, bloods, all this, and I carry it on a card, and I own the data. And through that NFT ways, we share it with the pharmas, the research engines, and all of these people with IoT devices who has live data and analytics, all the way through to, if I was almost going to have a heart attack, this thing has already called an ambulance because something major is happening to my system, or the doctor calls you. And that service is being built right now. We are already at beta for that. And it will be integrated even with all your pathology-related data, as well as your MRI and X-ray and radiography-related data, plus your health-related data for blood, your diets, and things like that. So that is another place where we use AI and intelligence, because no human brain today, within seconds, can analyze that. I don't care which professor or scientist they are, to analyze it like that, it's very, very, very difficult. So this is where AI ML really comes in, and especially the ML, the defense learning type of ML, where it learns because it's constantly feeding from the IoT devices of the patterns of what is happening with the person's health. So that's another thing we're developing. With that, I hope it's given you some flavor. I don't know, as a close and a wrap from me, but I'll leave you guys with one quote over here. This is very much my mantra for the last 20 years as well. I don't think anything like impossible works. I'm definitely not ordinary. When the fish is going one way, I'm the guy who's going the other way to look for alternative solutions. And Elon Musk says almost the same thing there. And it's great to have big disruptors. Yes, regulations are good. However, if you don't have disruptive serial entrepreneurs with experience, and I call them camels rather than unicorns, because we've been through the hard times, we've seen the ups and downs, and we will sail through it, and we won't let regulations stop us innovating, because regulations sometimes can stifle innovation. So we're going to muscle on and actually do this, and then adapt to regulations as they come about. If anyone wants to reach out at me, add me on LinkedIn, ping me an email. Love to talk to you. So if you're a startup in this area, love to talk to you. Thank you very much. Back to you.
Mr. Patel, thank you so much for this engaging talk. I've kept a few copious notes, so if you don't mind, when the next presentation is over, it will be nice to sort of engage in a mini dialogue, and I can play devil's advocate on certain issues and see where this dialogue takes us. So on that note, allow me to now take the pleasure of introducing Dr. Frederico Mesquita, partner at Lotus Investments. Dr. Frederico is the founding management partner at Lotus Investment Strategies. He was the founder of the first crypto fund focused on Latin America. He has advised companies and addressed several world-class blockchain conferences around the world on topics such as crypto investing strategies, trends and challenges for digital assets and blockchain, has enabled disruption and called inflection points such as the 2018 winter, DeFi, security tokens, and NFTs. He has over 20 years of serial entrepreneurship, foreseeing global tech and social trends. Dr. Frederico has held positions as a professor in several leading universities. Please join us for his speech. Thank you.
Hello, everyone. It's a pleasure to be here. Thanks for the invitation. I'm honored to be part of this forum. Academia and the real world should always work together, and I actually miss a lot the academic environment. And my background on artificial intelligence is almost a quarter of a century old, and it reminds me of programming in Lisp in late 80s. By the way, I have seen artificial intelligence promise at several points in my career, trends for the upcoming year, hot topics, and hot business areas for investments, and etc. And past couple of years, and especially watching the presentations today, yesterday, and the day before, it seems the time has finally arrived for real. I believe you are in the middle of a mini revolution, and I will try to cover a little bit more meta levels than my good friend Patel and said that we are not physically in the same city, especially if it was Greece, so we could share more news after these 2 years of pandemic. But nonetheless, This revolution is non-stoppable anymore. And it's a revolution that's a strong bet for democratizing the power of artificial intelligence. This revolution can be some way summarized by Web3 concepts and components. Democratize the internet is Web3. And how did we get here in Web3? Web3 actually builds on the browser-based document page that characterized Web 1, and then app development, content creation, social media, e-commerce that exploded during Web 2 that we live today, and that made possible giants like Facebook, Google, and Amazon to reach they have today. Web3 is hyper-integrated, is contextually aware, and especially it adds value to the equation. And value is the key word here. So we are moving from exchanging information to relationships to value. And the exchange of value today is centralized. You need third parties to send and receive money, to borrow and lend money, to be insured and everything else. But the question is, who will own and control this next version of the web? Decentralization, and this decentralization is empowered by blockchain and artificial intelligence, can return control and ownership of the user's data to users themselves. And this was actually the idea back in the early days of the internet. Since we have value as a centerpiece of this Web3, the heart of this decentralization process is decentralization finance, is DeFi. I will try not to extend too much to let us have our conversation and let Angelos play his advocate role, devil's advocate role, but I will try to cover a little bit of what's DeFi and what's the revolution going on, and some use cases in a meta level in relation to what Patel just presented. First thing to notice is that our traditional finance system is not efficient. Everybody knows that retailers still have to pay 2, 3, 4%, depending where they are, on every single credit card transaction. Stock trades takes a couple of days to settle, and stocks exchanges are only open 32, 35 hours a week. If you want to send money cross-border, it's expensive. International bank wires takes 2 business days, etc. Many of the institutional trades in the stock market happen in dark pools, and the list could go on and on. Lending can cost up to 100%, depending on the country you're based annually. So all these are inefficiencies, and all these are examples of a few characteristics of decentralized financial systems. They are the control is centralized, the access is limited, they are inefficient, they are lack of interoperability, even the saving rate is a problem. And what banks do is, as in any other value chain, they try to, as third parties, appropriate value and power. So DeFi can solve all of these. And let me clarify what we're talking about when I'm saying DeFi. DeFi are open source protocols, and they are collective owned by distributed communities. And they providing security from consensus with no central entity. So it seeks to build and combine open source financial building blocks into sophisticated products with minimized friction and maximize value to users. So we have two keywords here. It's minimize friction and maximize value. We could spend a whole day just saying and discussing all financial tools that DeFi offers, like investing, trading, loan borrowing. It's endless these days. Most of them are already in place, and even we are still in early in the maturity curve. The applications already in place have been already disrupting several of these applications. You can only to give an idea, the money, the total value locked on DeFi reached by December $250 million, and now after Terra and everything else, it's now under a little bit under 100 million, but still a lot of value. And this allow anyone to send and receive money from Brazil to India to United States at a very low cost, instantly, using everything that Murbach, for instance, is implementing over there. So if you want to tokenize your assets, and now you can use your digital assets or your assets that have a digital counterpart as a collateral for your lending, borrowing, or for anything else. So this is the power of DeFi. And we haven't seen even the tip of the iceberg of what can be done and what will be done in the future. All of this is powered by artificial intelligence. You cannot express enough how artificial intelligence play a key role for the whole revolution. Not only by securing some aspects of DeFi, like guaranteeing oracles, anti-fraud, anti-money laundering, and etc., but also in a second level, when we actually put the intelligence into the system by being able to learn and predict and act in ways that we are not even aware yet. And this is the future that I foresee, and this is the real revolution ahead. So when we have all this together, the whole global financial systems can be disrupted. It's not going to happen overnight. It's not going to happen without some fights. We need to accommodate interests of all the stakeholders, and of course, by stakeholders, governments, banks, and every other organizations. They are all part of these systems. So this is a process that's going to happen. It involves regulations. It involves innovation, and regulation should not stop regulation, but regulation actually usually is a good thing to give a framework where innovators, entrepreneurs can work and create, being sure or they are safe doing this or that. So this is a summary of what I see for DeFi and the main implications. I see a few trends going on for 2022 and ahead. Regulation is one of them, as Murbach said. It cannot stop, but it has to evolve somehow, and we can see a lot of moves in Europe, United States, and Asia on this. We can see NFTs that we just saw a few examples, and NFTing the whole world. 4 years ago, I don't know if Murbach was on the same conference, but I presented that NFTs would be the next stop, because it's obvious that if Web3 is about value and you can tokenize everything that's real into digital and then transact digitally cross-border, that's a few $1 trillion opportunity. The metaverse and how governance will change, because now we have DAOs, decentralized autonomous organizations, that are entities able to uh, uh, organize and manage all these new ideas behind. So what we see right now is this revolution going on. So Angelos, without further extend my contribution, I just want to summarize that DeFi, blockchain, and AI and artificial intelligence, for me, are the main aspects of what you're going to see in our next few years.
Frederico, Ruth, thank you both for being so passionate about what you do and what you believe in. And if I may speak for myself, you're preaching the converted. I believe in decentralization, and I believe that banking regulation has perhaps gone too far. Yet, I did promise I would play devil's advocate a little bit. So, given, I'm a believer in the good part and the good side of human nature, but given that human nature is human nature, where do we place a limit on this decentralization element? How can we coordinate it and make sure that we don't get carried away and that all these nice issues we talk about, quick transactions, cheaper transactions, ability for people with low net worth to enter into all this sphere and benefit from this. How can we guarantee, however, that it doesn't get too carried away and that fraud doesn't step in? Mru, would you like to start? Yeah, please.
Yeah, I can take that. First and foremost, Frederico, hi, how are you? Long time no see, 4 years ago, I think in San Francisco. Okay.
Yes.
So decentralization, the way I see it, where to stop it. And Angelos, you've been a gamekeeper to poacher now, I guess, from centralized bankers to now on the other side, you've seen the light and the benefit.
Absolutely.
However, I think I said it on one line. I can talk about this all day. I look for camels, not unicorns. What's happening is, sorry to say it, you get the younger crowd who's never managed money, who hasn't got a clue about finances, who hasn't got a clue about what ownership, trust, honesty, and all this. All they want to do is get quick, rich, and fast. So you get all sorts of valuations that are pie in the sky, not real, and this hype of crypto, blockchain, DeFi is taking them to stupid valuations, okay? And in that hype, what happens is they cut corners. And the places where they cut corners because of inexperience is regulations. So whilst I'm not saying that regulations are bad, regulations are there and it's good. But the main decentralized regulations one has to adopt is obviously the KYC AML stuff, which is a cliche. But if you take it to the next level is to make sure that people are not abusing the money for funding terrorism and stuff like that, which is, on the blacklist. So some of these
but you do need someone to centrally control that in order to make sure that this is not the case.
Centrally regulated, not controlled. Big difference.
Well, today you can talk about regulation, but it's not controlled. It's regulated and not controlled.
Today there's no regulation on decentralized exchanges.
No, I'm talking, if you talk about the pure banking side, the conservative part, the centralized, the financing. Frederico, do you think it's regulated or controlled, Frederico? What would you say? Is it regulated or controlled?
Well, there is one piece that's very important to mention. A good part of regulators came from the banking. So if you look at some of the regulators in the US, for instance, 6 out of the 9 are from former bankers. So sometimes it's regulated, but it's regulated by the same people that are being regulated. Even if they are not in the systems anymore, their friends are there, everyone else is there. But on the other hand, I would like to mention that even regulation doesn't need to be exactly centralized, because, for instance, you can have discussions like the Europe Parliament, bringing together all stakeholders, bringing together innovators, startups, banks, government, universities, everybody to contribute and try to create a framework. And what I believe is that the evolution will be so fast that you will not be able to write fine prints about everything. I like the intent of Europe.
The less wealthy from the super rich. That was one of the terms you used, protection of your ecosystem from the super rich. How do you protect from the super rich, meaning economies of scale and buying things in scale and entering into investments into any system in scale will bring benefits to whoever does it, no matter how you see that. How would you keep the super rich for targeting your ecosystem and trying to benefit from that scale?
Very good question. I mean, I didn't have too much time on slides. Can I share this slide?
Sure. If it's going to stir things up, why not?
I want to stir things up. I don't like boring debates.
There you go. Makes three of us, I think.
There you go. So can you see this?
Personally not, but it could be my vantage point here.
Okay.
There we go.
Can you see it?
Yes.
Yes.
Okay.
It's your cover page from your presentation.
No, it's this one now. Actually, I didn't show them this slide. Sorry, my bad. I didn't share this because that's the whole ecosystem. Let me talk about it. Switch the slide off. Let's have everybody on the panel. So it's the whole ecosystem from social impact, ESG, neobanking, distributed and decentralized exchange, centralized exchange, all the way through to social impact, social community building, blah, 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 insurtech, health tech, wealth tech. So how do I protect it from the big rich guys? I limit the big rich guys to come in. So everybody gets a share of the whole tokenomics of if it's revenue for them to earn by doing a like, share, comment, all the way through to if someone, a little guy in India, Kenya, wherever it may be, to post a little music video, they get majority of the revenue rather than what currently happens where the tech platform takes majority of the revenue.
So, Mru, how can you keep me at bay if, as Angelos, I want to wear 5 different hats? So I'm incorporating a number of companies and entities, and I come in on a small scale, but through a number of entities that I control, and I try to then target your ecosystem. Since you don't want to regulate anything, how do you keep someone like how do you keep someone like Angelos who wants to really target and take your ecosystem away? How do you keep me at bay?
Fantastic question. Regulation, I didn't say is bad. I said regulation to protect the customer is good. So in your scenario, how do I keep people like you away? Again, this is where AI and ML comes in. And this is where KYC comes in. Same guy, photograph, video KYCs, proper AML, proof of address, proof of funds, mobile numbers, text, that. So if you got the time and effort to create clones of Angelo through 50 different pictures with 50 different mobiles, 50 different addresses, good luck to you.
I can have my employees. I can have employees in my
different
company.
individuals.
Yeah, but same
Different
entity.
individuals.
But it could be the same entity. Anyhow, I just wanted to play devil's advocate to get Frederico's response to that.
Yeah.
But again, it's same entity, you see.
A little bit different, but I think that nobody's naive to believe that banks and the super rich or the ultra rich will not become richer, and they will not appropriate value from anything that we create, being centralized, decentralized, blockchain, artificial, doesn't matter. They will make more money. This is not a problem of DeFi and blockchain or artificial intelligence. This is inherent of capitalism. But what I believe we can do is, first of all, I do not believe that we will kill the financial systems and all the incumbents like the crypto kids think. That's utopic.
You've already established it's
that
dinosaurs and camels, so you can't kill a dinosaur or a camel.
Exactly. But I believe we can do one thing. You don't need to actually protect the not so rich from the rich. But once you can give the same opportunities for everyone, then you are already closing the gap. Because one thing that makes rich people more rich is they have access to opportunities that nobody else has. They have access to information and knowledge that nobody else has. So if everybody has the same information, if artificial intelligence working behind, integrated within the systems, can provide intelligent knowledge. Knowledge is always intelligent, and my PhD is in knowledge management, but then everybody is in the same playing field. And maybe I'm not going to make as much money as Elon Musk, but at least the gap will be smaller.
Let me give you an example, Angelo.
Okay.
One of the wealth thing we are doing using AI. So this is the third bot we are creating now, where it's very much AI ML driven for trading. This has been available, as you know, to banks for at least 3 decades that I know, all right? And they make that, the Goldman Sachs and Jamies of the world have been doing that for their client. They top slice most of it, give their ultra rich a slice on performance, but a lot of it's kept in-house, to be brutally honest, okay? Our model in that AI trading bot is whatever we get, majority goes to the client. So you could start with even $1,000 and enter exactly what Frederico said, giving access to information, wealth creation, financial inclusion to the smaller players, the $1,000 guys, rather than saying you can only enter this with 60% returns if you're $1 million plus client.
I think you've raised a number of issues already for our next year's AIIA forum, because no matter what we say, all these ecosystems have to make money as well. So you will have to tell us how much of that you will give away and how much the ecosystem will rightly keep, because all of us are in business for a profit. Thanks for a really engaging discussion, for your passion in your ideas and speeches. Thank you for your time. Dear audience, thank you for being with us for one more session. This will be the conclusion of the last discussion. Thank you.
And that was the best ending of a very long 3-day conference. I think that this debate was really vivid, and we need to continue. Thank you, all for being with us for those 3 days. That was a very good conference, and that's what we get from our audience. Attendance is very high. We will issue all data, marketing report, publicity report, minutes, moments will be uploaded on the website in the days to come. So please follow our website during the next week, and you will see everything uploaded there. Plus that you will be able to see the replay of the conference. It will be available on our website for you who would like to watch parts of the conference that you missed during the live. It was a very long conference. I think we couldn't see it all. A few people managed to see it all, but there are people who tell us that they would like to see some sessions, and they will go back. They will come back to see the replay. So can we see the Silicon Valley now? Here we are.
Despina, Periklis, Periklis, you'll have to, and the rest of you there, you'll have to show us how AIIA can really make a 3-day forum palatable in a few minutes for people to digest. So that's your next project.
Yeah, I think for today, there is no more dialogue. There's no more discourse, no more provocation, Angelos. We're not going to follow your example. But Silicon Valley has concluded its participation, and we're very grateful to all presenters and panelists. And I will pass the baton to Woody Gibson to give us the final command here, as he represents Silicon Valley literally. Woody, the floor is yours for the final command.
Oh, this is one step forward for AI from Silicon Valley. And we hope we do this every year. That's good. And Silicon Valley is here to help the world, and it looks like Greece is too. Thank you very much for your attention. And the whole team is here, NASA, Silicon Valley, the university, the entrepreneurial, and thanks to this young lady. She was the powerhouse. She's from Malta. So all the best, and good day from Silicon Valley.
I do want to add on to that. It wasn't just me who played a part in organizing this whole conference. A year ago today, Despina sent a message to me about this conference, and we started our group chat. And from that day on till today, the team that everyone had been onboarded has been working so hard to get this together. The tech team, the communication team, the PR team, everybody, to get the venues, the virtual conference together. And so I'm very happy to see that it all came together very well. And I'm sure Despina is also very proud for her team as well.
And this is Mark, just a final comment also. I really want to thank Despina, Angelos over there, our Athenian colleagues, as well as Hadis and his wonderful technical crew over there, and Eric and his technical crew on this side. And you guys glued everything together. It's a superb job. Technically, we are very grateful for that. Thank you, everybody.
Thank you. Thank you from Athens as well. It's been a pleasure cooperating with you, and we will continue. Zarina, you graduated, but you are still in the team.
Let's keep passionate. I
Yes.
think that's the concluding message from Athens. Let's keep passionate.
It's a beginning, it's not an ending.
Thank you all, and have a great weekend.
Bye.